All right. Sorry, I forgot to turn the screencast-o-matic on time, and we have sort of a small crowd today, only 8 students so far. And what we were just talking about before I forgot to turn on the screencast-o-matic was the fact we are really batting along really rapidly here, and we've got 3 weeks to go and only less than 3 chapters to do. So what we want to do then is let's go on, and today we'll finish chapter 20. And rather than rushing through it so we can do a lab on chapter 20, we've got time. So we'll finish chapter 20. There's plenty here. But I think we can easily do this in just class time. And what we'll do for lab today, rather than doing whatever lab it is it lab 7 that's out there? I think that's it. Let's hold off and we'll do lab 7 next Tuesday. Okay? So we'll finish chapter 20 today, and then we'll hold off and start on 23 next Tuesday. Okay? And we'll do lab 7 Tuesday, and oh, here comes Gerald, so let me get him in if I can find there he is. Okay, Gerald's here. Okay. Okay. All right. Okay. Gerald, I don't know if you realize it, but you're muted now. Good. All right. Gerald, I was just talking with the others, and what my proposal is, and it sounds like others are in favor of it too, is we've been batting along as if we were on fire or something like this, and we're pretty much ahead of schedule. So what we're going to do is just finish chapter 20 today, and I think it won't even take us our full 2.5 hours to do that. And then rather than starting 23, we'll do a pause then, and what lab will be today is going back over for anyone who is behind in the labs. If you have any questions, we'll do a review of that. And if you don't have any questions and everything gets done and you're happy, then we can leave early, and that will give you a chance to take advantage of the day to work on those labs. And here's the part that I'm kind of most concerned with. I have graded 2 tests, and I think that's the only 2 tests that I've received. Okay, so graded 2 papers, research papers. That's the only 2 papers I've received. So folks, you need to be working on your research papers. So that's the second thing. If you don't have labs you need to catch up on or make up today, then I would suggest using the latter part of today's class to be working on your research paper, because we're running short of term now. This is the end of week 5. We got week 6 is next week, week 7 is the following week, and then week 8 is the last week. So we got 3 full weeks to go and less than 3 chapters to do. So what we'll do is today finish chapter 20. Then on Tuesday we'll start chapter 23 and do the lab for 20. Okay. Then we'll spend Thursday finishing chapter 23. And we may postpone its lab also until the following Tuesday, and then do chapter 24 basically that week. Okay, and the lab on 23, and then we'll wind up with finishing up 24, doing getting labs caught up, and then basically your final exam will be that last Thursday. Yes. Okay, I believe I posted out there through test, um, let me add them up, 14, 15, 16, 17, 18, 19. I've posted 6 tests so far. Is that right? And we've only got 3 chapter tests left to go, chapter 20, chapter 23, and chapter 24. So only 3 tests left to go, only 3 labs left to go, because I think we've done 6 labs so far, and we've got 3 weeks to do them. So basically, we're going to finish chapter 20 today, but we won't do the lab today. We'll wait and do that on Tuesday. So that means we'll only get started on chapter 23 on Tuesday, and hopefully maybe finish it up on Thursday. If we don't finish it up on Thursday, we'll definitely finish it the following Tuesday, have the lab for chapter 23 that day, that will be Tuesday, and probably get started on 24 that day, and then do 24, and then we'll start wrapping that up early the following week. So we've got some time here. Let's stop and breathe a little bit, and that will give y'all a chance to work on your research papers and get caught up some of your labs and maybe some of your tests as well. Okay, so how does that sound for you? Are you with your, yeah, okay. I think that would be the fairest thing to do. I see no reason to rush through and get everything finished and then have a week of nothing to do. It would be better to sort of spread it on out, and that way there's just no rush. Okay, well then if everybody's sort of in favor with that, then let's go on and get started in chapter. Well, first, do you have any questions, issues, concerns, problems, anything whatsoever? Doesn't have to be physical science, it could be anything. Okay. Well then let me get the screen share set up, and we're chapter 20. We're starting in the very most important part of physical science ever, and that is soils. Okay. Now what? Let me make sure nobody else is coming in. I've got 9 students here. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. So first thing I've got to do, you can't see this, but I have a taskbar that's covering a whole bunch of the slides. So I'm going to move it down as far to the bottom as I can and get it out of the way. And I'm going to scoot and Darius over a little bit to the right because he's blocking a little bit of the slide. Well, several of you are. I just picked his name. All right, and let's pick up from current slide here. And I can't get it to click. There it goes. And it just went way past. Okay. Now, maybe a quick review of what we've done so far in chapter 20, shaping the Earth's surface. Now, what we're really talking about here is wearing down the Earth's surface. That's what they're meaning by shaping. Because all these rocks were being formed in the last in the last chapter, you know, building mountains, building this and building that, building the Earth's surface. Here is where we're going to talk about. And these aren't separate issues. They're all going on at the same time. We're also wearing down the Earth's surface, okay? And we do that through 3 types of what they call weathering, okay? And that's physical weathering, actually wearing it down. I can remember when I was an undergraduate, the dorm I lived in for the biggest part of the time was right next door to the cafeteria, which was nicely convenient, except it was a pretty lousy cafeteria. But anyway, I remember that cafeteria had been there forever, and I remember always noticing the step going up to the cafeteria was worn down, so many feet had trod on it for so many years. Okay, you're constantly, no one ever realized they were wearing any little bit of it off, but over and over and over, repeated people walking on that, they really were wearing down that step. It had taken decades for them to get down to that point. Same thing is true of rocks. Even the hardest rock, over time, it's going to be worn away, worn down. Physical weathering, like walking on the step, just wearing it down, grinding it down. Chemical weathering, now that would be like if you poured acid on the step and it dissolved some of the cementing agents. Well, we don't go that far, but those things that we did talk about, oxidation, that is always happening. Acidification, which the book called carbonation, is always happening. And then hydration, dissolving things away, that's always happening. I don't know if you've ever noticed someplace, our garage right out here to my right, we don't have gutters on the front part of it that does into the driveway. Where the water drops down and hits and splatters right there, you can almost tell the concrete, the cement part of it has been leaching out very, very slowly from hydration. Okay, and you see more of the rock, the what do they call that, aggregate that's left, and you can see that is hydration, dissolving away materials. Okay, so those chemical processes have been happening. Also, we've had biological processes. We talked about roots, how they secrete an acid, which is a chemical, to break apart soil particles or rock particles and extract the nutrient that they're trying to get to. Microorganisms are always attacking whatever is there. I just happened to notice, I have noticed for a while, but recently noticed again, the lichens growing on we have a retaining wall holding up the backyard out of our patio, and you can see things are growing on the rock that are obviously feeding on the rock slowly, but over time they'll disintegrate and break that down. Well, what's left over? Is it all a bad process for your rock to be wearing away? No, it isn't. Because if it weren't for the wearing down of rock, we wouldn't have soils. Soils are mixtures of unconsolidated. Now, what does that mean? Not part of a rock anymore. They're unconsolidated. They're not consolidated into a rock. So mixtures of unconsolidated, weathered, remember we called that weathering, physical weathering or mechanical weathering, chemical weathering, biological weathering. So unconsolidated, weathered earth materials mixed with a substance they call humus. Now that's not being funny, that's not humorous, nor is it that good Mediterranean sauce that you eat with pita bread. Hummus, that's 2 M's, this is humus. What in the world is humus? Well, here's a definition for it. Altered, and we'll come back to what is altered, decay resistant, or at least mostly decay resistant, plant material. Okay? Now, one thing I like to do in our yard is I like to mulch. Okay? And we'll talk about that a little bit later. What do I use for mulch? Well, I have a bag still left down there, pine bark. We also have used cypress bark. We've also used pine straw. Okay? I used to, before my wife made me quit it, suck up all the leaves from the yard rather than putting them in bags and out on the curb. I ground them up in a device called the chipper shredder vac and shredded them, and then used those to mulch my beds with. So those were leaves and sticks and acorns or whatever else was there on the patio, on the driveway, on the sidewalks, or even in the yard rather than putting them out on the curb and someone hauling them off, I ground them up and use them as mulch. Okay?
That's a good idea. Why did she tell you to stop?
Because I'm old and it was taking me too long. And she was afraid I was going to wind up, overdoing it. So she has hired some people to come in, and I'm afraid they don't do it as well as I did. But yeah, I love doing things like that. Yeah, I agree with you. It's a great idea. So what was I doing? When you're mulching, basically what you're doing is covering the top of the soil, okay? And the microorganisms that I talked about before start eating away at the mulch, okay? And whether you mulch or not, nature mulches too, by the way. And anyway, when they're through, what's left is altered plant material. It no longer is pine straw, or no longer is pine bark mulch, or cypress mulch, or even leaf mulch. It's what's left over. What's left over is the more decay resistant part. Because guess what? Those microorganisms eating away at that's what we call the decaying process. That's what decay is. Microorganisms eating away at basically plant material. Okay? And what's left over is usually dark and submicroscopic. Okay? It's so small you can't see it. Now they say plant material. I bet you there's also some animal material left in there as well, because sometimes in the flower beds, and if we do have garden type area, I'll mix in some. You buy it from the Home Depot or somewhere, black cow or something like that, which has decayed animal material too, basically manure. But what is animal manure? But basically broken down plant material, because the animals eat the plants, okay? So that's why they call it plant material, but it may have come through or from an animal as well. Now, if I were to ask you what a good rich soil looks like, how would you describe a good rich soil to me? Any of you who, very dark. And what you say?
Yeah, black.
Black, exactly. You know what? That's not plant material. I mean, that's not soil there. Well, it is soil. That is your humus. The humus is usually that. You could have a sandy soil. Now, what's right or wrong with the sandy soil? Well, sandy soil, just because the sand is large particle size for a soil anyway, it has large pore sizes, water just goes right through it. The roots barely can get anything out of it. And because they're large particle size, the roots can hardly get any nutrient out of it. So a sandy soil is usually not the best soil to try to grow something in. But what do? You add some organic material, some humus to it. And what the humus does is take up some of those pore spaces, so now the water doesn't go through as fast. It still goes through, it doesn't puddle or something, still goes through but not as fast, leaving it there for a little bit longer for the roots to take advantage of. But it also uh, it consolidates the soil, and that's what I'm sort of talking about. But it improves the water holding capacity of the soil. It's not really adding that much nutrient. It does add some. That dark soil will contain a little bit of nutrient. Like leaves always contain some magnesium. Okay? They'll contain some other things like calcium. The pine bark mulch, mostly calcium. They have some nutrient value in them, but by and large, all they're doing is improving the water retaining capacity of the soil. Now that's of a sandy soil. Let's take a clayey soil. I don't know if you have those in your backyard. We sure do. And those clay soils, the problem with them, the clays are such tiny, tiny, tiny little particle size. I don't have a dime up here with me, but you can picture the thinness of a dime, right? If you were to take that dime and slice it, okay, somebody else is trying to come in. I can't see who it is. Labrina, good deal. Okay, Labrina is coming in. Okay. Uh, Let me get her marked here. There she is. All right. And I just ran into, oh, here's somebody else trying to come in. Well, I thought I got her in, but evidently it didn't. So Labrina is coming in. I marked her here, but evidently when I clicked on her name, it blocked it and didn't let it do. So I think she's coming in now. And by the way, I don't know if this is a timeout here, okay, from soils. We'll get back to that in a minute. I'm very slowly, now that I've got spring schedule done, I hope, knock on wood, and these other big things, most of them taken care of, I'm finally able to go back and start going through some of my emails and get caught up a little bit on emails. And some of you may have noticed that stuff that you submitted a long time ago, I'm just now acknowledging your receipt because they got buried in a bunch of other emails. And I've been going through those and finding those things I had been missing. And one thing I found, y'all know, do any of you know Deja? She was in the class, Deja Gray Miller. I ran into the email. I think I had seen it, but it didn't register with me who it was talking about because it was right about early in the term. I think she had surgery, so she's been out for 2 days and is not here today either. So she's been out about a week and a half now. Situations like this is another reason I want to slow down a little bit and let some people catch up. There was a couple of people who have been very late coming into the class, and this is such a short term, mini term, that I wanted them a chance to catch up too. So I don't know if any of you know Daisha, sort of help her out some because she's had surgery. It didn't sound like it was a major type thing, but it still incapacitated her for a while. All right, so let's get back to that. So what does this do to a clay soil? Clay soils, I was saying, if you took a dime, a thin little dime, and sliced it in that thin dimension there, 1,000 slices. I mean, I can't even imagine that. You would be able to see through them. You wouldn't even hold them up. They'd fall apart, okay? But that is 1 micron. 1/1000th of the thickness of a dime is 1 micron. The largest clay particle you'll ever see, and you won't see it because they're submicroscopic, is 2 microns. The largest one has a dimension of 2 microns. Okay, 2 of those thin. So what we're talking about, a clay is so small particle size, they pack together like crazy. And then it's hard for water to make its way through. So whereas a sand, water just flows through too quickly, the plant roots can't get to the water in time. Okay, it doesn't hang around long enough. Clay soil, on the other hand, with very small particle size, it is hard for water to make its way through. Oh, somebody else I think is coming in, but I can't see who it is. Please get out of my way. Well, let me go down here and maybe I'll do it that way. Okay, it's a telephone number. Okay, does anyone remember who the telephone number is? Don't want to call out the. It's who? Brianna. Okay, got it. I've lost my pen. There it is. Okay, let me get you here. Now, I did get you in, right? Okay, good. So Brianna's here. Okay. Now, is anyone else waiting to come in? So that gives me 11 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So I'm up to date, I think, on students. And Brianna and whoever else has come in recently, we had started talking about soils, but before we started talking about that, I was proposing for the class, and most seem to be in favor of it. We're going to slow down just a little bit. We have been going at a breakneck speed, and we're really a bit getting ahead of ourselves because we've only got this chapter 20 to go, and 2 more chapters, 23 and 24. And yet we got 3 weeks to go after this week. So today we're going to take our time but go over chapter 20 nice and thoroughly. But when we finish with chapter 20, we're going to stop. Okay? Whether that's before lab time or after lab time, wherever we finish with chapter 20, we're going to come to a stop. And then what we're going to do is it's going to be open mic night. Okay? Any questions you have on any of the past labs, and I want to say the test too, but I'm not going to answer any test questions in class, but I'll answer questions about the test if you have them. And I want to give you time to get things sort of caught up. Another issue is only 2 people have submitted papers so far, your research papers. You've only got 3 weeks left. So if you need to, take some of today's time and start working or continue working on your research paper. If you haven't done all your labs, get working on some of your labs. I'll be here to answer questions if you got them. If you're behind on tests, take that time to work on your tests. Now, I'm not going to answer questions from the test, but if there's anything that was puzzling you, you're not sure what the question's asking, I will clarify for the test questions. Okay? So that's what today's going to be. We're going to finish chapter 20 and then come to a screeching halt and do a little catch up. Then next Tuesday, we will start chapter 23 and go for an hour or 2.5 hours into 23, stop there, and have the lab from chapter 20, the one that we finished today. And then Thursday of next week, we'll finish chapter 23, and we may do the same thing over again that we did this week. Have it as an open mic night, open time for you to ask questions and get some things caught up. And then the following week, which will be week 7, we'll start chapter 24, and after 2.5 hours, stop and have the lab for 23, and then continue on 24 on Thursday. Probably come close to finishing it, but if not, then the last week we'll finish chapter 24. We'll have the lab for chapter 24, and then the last day will basically be your final exam day, and catch up anything else that you may have. So how does that sound to you? Okay? Now, one reason I'm sharing this, we're probably going to be finishing early today. And if we do, if anyone's coming in really late, we're already going to be through. So if you're in communication with anybody that you think may be waiting to come in for lab today, go on and get in touch with them and say, hey, we're probably not going to do a lab today. We're probably going to be catching up old work. So if they want to be counted present today, they need to come on to class. So if you know anyone like that. All right. So for those of you who got here, we're in chapter 20, Shaping Earth's Surface, in section 20.3, Soils. And that's where we are now. And we were just talking about this. So I was talking about clay particles are so small, so tiny, they pack together really tightly, it's hard for water to penetrate through a clay. So what do? You add humus to it. You add this altered decay-resistant plant material, and what that does, it sort of spreads the clay particles apart a little bit. It makes the water more accessible to go through, whereas with sand, it sort of slowed down the water. In clays, it sort of gives water a better path to go through. And clay particles hang on to water really tightly. The humus releases it fairly easily. It doesn't let it drain through, but it does release it. So if a plant root comes up and tries to suck water from a clay particle, that's got a lot of energy is taken up doing that. Comes up to a humus particle, it can suck out the water much more easily. So humus, even though we think of those dark soils as being rich soils, it's not a nutrient richness, even though there is some nutrient there, and I don't want to minimize that, there is some. The major thing it's doing is making water more available to plants. That's what that good dark rich soil is doing. It's not any richer necessarily, it's just got more of that humus in it, which makes the water retaining capacity of the soil easier for the plants to get. Now, let's look first at the weathered earth materials. Those weathered earth materials would include sand. Now, I told you what a clay was. A sand is if you took two of those dimes and put them together, not slices, but two dimes, that would be 2 millimeters. Anything less than that size is a sand particle, down to the next one. Then you get way down to the clay particles, and in between that you have what they call silt particles. Now, clay particles are submicroscopic. There's no way you're going to do anything with them but fuss at them because they're usually hard to manipulate and deal with. But here's how you tell sand from a silt. If you have a sand and you rub it between your fingers, you feel the grittiness. If you have a silt and rub it between your fingers, it feels like flour, like talcum powder. It's no grittiness whatsoever. That's a silt particle. Clay particles, you could have it, you rub it between your fingers and it gets down into the pores of your finger. I mean, you don't even notice it's there. It just makes your fingers turn color. Okay, so that's the thing. It's a mix. The weathered earth materials would be sands. Now, a lot of those sands are quartz, admittedly, but not all sands are quartz sand. Any particle size that's of that size, weathered material, would be a sand. It doesn't have to be quartz. Now, when they say quartz, though, that also implies very low nutrient value, because if you think about it, quartz is made up of silicon dioxide. Well, plants don't need silica. They don't need, yeah. So very poor. Okay, Jackson, I think, is here. If I can get the thing to disappear, well, I'll do it down here. Come on, here we go. Jackson's coming in. So let me let Jackson, he's coming in. Let me mark him present. So that indicates 12 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, got it. Okay. Now, Jackson, I hope you're in now. Good deal. Sorry, the rest of you, but let me go over this again. What we've decided to do, I propose it, and the rest of the class is sort of going along with it, okay, is we've been busting it, okay, really getting things done much faster, it seems like, than any other term I've ever taught this. So maybe it's time to slow down a little bit, okay? So what we're going to do today is finish chapter 20. That's shaping Earth's surface, okay? And then at the end of when we finish this today, rather than having the lab, even if there's time for lab, what it's going to be is a time for you to catch up other labs, other tests, or work on your research paper. Okay? It's going to be sort of a free-for-all. Whoever has questions on anything can ask them. Anything I can help with. I won't answer test questions, but I will answer questions you may have about the lab stuff, or if you have questions about the test, things you don't understand, I'll be glad to try to clarify those questions. I won't answer them for you, but I'll try to clarify them. And yes. Okay. And it'll also be a time, if you don't have any of those to work on, then I suggest that you work on your research papers. Now, some of you may be ahead on it all. If you are, then you just have free time to catch up on other classes. But most people have some things they are still behind on. So it'll give you a time to sort of catch up. Then next Tuesday, we will start chapter 23, because we should finish 20 today. We'll start chapter 23, go for 2.5 hours on 23, stop there, and we'll do the lab for chapter 20. Okay? Then Thursday of next week, we'll probably finish chapter 23. And by the way, I'll give you the test for chapter 20 whenever you want to have that, either at the end of the class today or probably after we do the lab on Tuesday of next week. And then for 23, we may do the same thing next week we're doing this week. Just have Thursday is finishing up 23 and then pausing and having the lab for 23 on the following Tuesday, because that will be week 7 then. This is week 5, next week is week 6, the following week is week 7. And we'll get started on chapter 24, and by the end of the week probably finish 24, and then if there's time we'll do 24 lab. No, I don't guess so. We'll probably wait until the following week to wrap up 24 and do the lab, and then I'll give you the test for 24, and then I'll give you the final exam on that for that last Thursday. So we've been going at breakneck speed here, so we're going to kind of put on the brakes a little bit and give you time to start catching up things you might be behind. How does that sound? Okay with it? All right, so let's move on. In addition to the sandy materials, which has generally large pore size, doesn't hold water well, and if it's quartz sand, which a lot of it is, it's not very nutritious either. Okay, the humus improves the water retention capacity of that and adds a little bit of nutrient. The clay minerals tend to be much richer in nutrients, some of them anyway, but they don't allow water to go through quickly. The humus allows water to pass through clays more easily, so it improves the plant availability of water. Now, the next thing listed here are the metal oxides. The metal oxides are basically, there are others, but the main one is iron oxide. And if I were to ask you what color Georgia soils are, what would you say? Georgia red clay. We call them red. Why? Because they have iron oxide attached to the edges of those clay particles. Clay is usually a grayish, whitish, colorless kind of material. Clays are made out of that. And yet all the clays, or most of the clays we see, are red clays. Why? Because they have metal oxides on the edges of the clay. That's what gives them color. So there are the metal oxides, and then there's the salts. Now what are the salts? Most of the time we hope those are nutrient salts. Some of those would include your phosphates that we talked about, an essential plant nutrient, maybe potassium nitrate or potassium chloride. Those would be salts. Ammonium nitrate would be a salt. Some of those contain really great amounts of nutrients. Others, like sodium chloride, no nutritional value there to speak of at all. So the salts can be beneficial, they could be harmful, or they could be very neutral. Okay, but all soils contain some of these salts, usually dissolved, but then when it dries out, then they desiccate and become part of the soil material. Now, what's the ideal soil? That would be, they name it a loam. It's a soil containing varying amounts of sand, the large particle size, which means large pore size, silt, which are small particle size, small pore size. But I'll just tell you right now, there's just not that much silt in the soils in the southeast. There's some, of course. And clay. And clay is very small particle size and very hard for water to penetrate. Mixed with an abundance of that altered plant, decay resistant plant material, humus. That makes an ideal soil. You have mixture of soil particles, which means you have a mixture of pore sizes. That means water runs through it okay, but not rapidly. That gives the roots plenty of opportunity to get the water they need and to extract the nutrients they need. Okay? That's the abundance of humus increases the soil's water, or the plant availability of water. That's the main thing it does. Now, This is sort of a misnomer here. They say a loam is also known as a topsoil. Well, if you notice, the author of this book is from Arizona State. Out west, that may be true, that maybe most of the topsoils are loams. Here in the southeast, not so much. Okay, let me let Diana in. She just got here. Diana is here now. Okay. Turning out to be a pretty good class size today. We're still missing Avius, Sancho, Amari, Deja. Like I said, Deja had surgery, I think it was, and Drew. So hopefully we'll be getting some more of those in as we move along. Okay, now Diana, if you can hear me now, sorry for the rest of you, you've heard this several times before. Sort of changing gears a little bit here in the class. I realized as I got to thinking about it, we're batting along way too rapidly in this class. We're going to run out of material before we run out of term. So we're going to put on the brakes a little bit to let y'all sort of get caught up. We're right now in chapter 20. This is the seventh chapter that we will have covered out of 9 chapters, and we've got 3 full weeks left. Okay, whoa. No reason for us. What's that again? Yeah, I know. So we're really moving a bit too rapidly. So what we're going to do is put on the brakes a little bit. And today, what I'm going to do is finish chapter 20. This is the 7th chapter out of 9. We'll finish chapter 20, but stop right there. We will not do the lab for 20 today. What we'll do today for our lab time is have a catch-up time. Okay, that not mustard, but no, I'm just kidding. A time for you, if you're behind in some labs, if you have questions about those labs, I can go over some of those things with you. If you're behind in tests, only if there's something that you're not understanding about a question, not the answer, but what's not understanding what the question is asking for, I can answer those kind of questions. I won't give you the answers for the test questions, but if you're not understanding what the question's asking, we can do that. If you've got your labs and your tests caught up and you haven't got your research paper done yet, then you can work on your research paper. So this is sort of a day for you to say, okay, let's take a breath and get caught up things you might be behind. Okay? How does that sound? I hope that's okay. So we're talking about soils. We're in chapter 20, Shaping Earth's Surface. 20.3 is soils. Okay, we having trouble getting through this just because people are coming in one at a time, but that's okay. So here's why I was arguing that a loam is not always a topsoil and a topsoil is not always a loam. A topsoil is exactly what it says. It's the top layer of a soil. That's what a topsoil is. Now maybe out west in Arizona and California, maybe most of those topsoils are loams. If we had our druthers, we'd probably like for them to be loams. But guess what? Here in the southeast, sometimes our topsoils are measured in millimeters or inches, whereas I lived in Nebraska for about 5 years while I was doing my graduate work, and there they measure the topsoil some places in feet, not in inches, okay, because they have such an abundance of topsoil. Okay, down here we don't. We've had too much erosion. We're going to talk about that coming up in this chapter. We've lost so much of our topsoil. So our topsoil is whatever's on top. That may be clays, it may be sands, may be anything. In the best of all possible worlds, that would be a loam, because that is the most strategic and friendly environment for the plant roots to live, is in a loam. But that's why they say, also known as, well, in the best of all possible worlds, your topsoils would all be loam. Most of the time, we're not in the best of all possible worlds. Now, what's the subsoil? That's the soil underneath the topsoil. Now, some features of the subsoil. less fertile than the topsoil. And here's one of the reasons. Less humus than the topsoil. There it is right there. And again, humus doesn't mean high fertility. It means the plants have more opportunity to take advantage of the fertility that's there. So it's usually less fertile, mostly because there's less organic matter mixed in with it. It may contain more rocks or mineral accumulations. See, the mineral accumulations may be where your fertility is. So this is sort of contradictory here. But what they're saying is it's harder for the plants to get that nutrient in the subsoil because it's really packed together. Okay, the plant roots have a hard time penetrating it. Sometimes it's more acid, so the plant roots get down there and they don't even want to go there because of the acidity. And it's hard to get your lime, which is your acid reducing material, to penetrate into the subsoil. So there's lots of reasons why the subsoil is less fertile. It may not be because it has fewer nutrients. It may have more nutrients. But the thing is, the plants can't access those nutrients as easily as they can in the topsoil. May contain more rocks. The rocks may be fairly rich in nutrients, but they can't get to them because they're rocks. Okay. And the main thing is it contains less humus. That keeps the water from flowing through it as easily. It makes it harder for the roots to get there and the roots to access what fertility there is there. All right, I don't know what the noise is. Let me see. Is anyone else trying to come in? I don't see so, but let me check and make sure. I do have 13 people here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, that's right. All right, any question on soils? Here is the most important section in the entire course, maybe in your entire 2 years at college. No, I'm just kidding. And it's one slide, okay? Less than one page. In fact, less than one column of a page. And that's all they dedicate to soils. Shame on them. There is a little concept applied here, city weathering. You can read that if you'd like. It's a little on the lame side in my mind. But now we get into what is the biggest hazard of soils, and that is, if the thing will advance here, that is erosion. Now sure, rocks break down. And when rocks break down, they tend to get carried off. Okay? That process is called erosion. However, when a soil gets carried off, that's not a good thing, because that's what sustains life. Soil is where our plants grow. Plants are what our animals eat. That's our food chain. Okay? We've got to have them. Erosion breaks that chain. So what is erosion? It's any mass movement of soils or other solid earth material. It could be boulders going down the hill. That would be a landslide. Okay, it could be any mass movement, but we're most interested in soils, the mass movement of soils. Erosion, all but one type of erosion, and they don't say that here, but all but one type of erosion is caused directly by gravity. And guess what? Gravity is everywhere. So you're not going to stop erosion because you can't stop gravity. Gravity is the force that pulls everything toward the center of the earth. So sure enough, erosion is caused directly by gravity. Now, it's exacerbated by what we do, okay, but it's caused by gravity. Two types of gravitational movement, mass movement. The first of these is what they call soil creep. You don't see it moving, but it's a very slow movement of soil down a steep slope. Just inching along because gravity's pulling it down. Not fast, nothing major. Let's see if they have a slide on that. Sorta. Okay. Your chemical, physical, biological weathering is happening up here. You're breaking down the solid rock, making soil, but because of the slope here, the steep slope here, the soil gets carried down and it gets thicker at the bottom. Now, these trees are illustrating the fact that soil creep is happening. I've never seen a tree to this degree of a bend in it, but I have seen them that are sort of a little bit bending. They're always reaching up toward the sun, but if the soil is moving against them, that could be pushing them in this way. Their tap roots are down here, but the soil is creeping down, pushing them over. I've never seen it to that degree. You'll sometimes see it maybe a little like this. I think this is an exaggeration, but that's what soil creep is. Very slow movement of soil down a steep slope. Now I can remember way back, I don't know which grade it was, early grades, when we first started getting into science a little bit. I can remember whatever book it was talking about how the farmers in Europe, especially those in, say, Switzerland or places like this where everything is really mountainous or hilly. I think it was talking about France as well, and parts of France anyway, that what they would often do is take out the soil from the bottom of a hill, haul it back up the hill, so they were actually trying to reverse the soil creep. They knew it was happening. They were trying to reuse that soil over and over again. I thought that was pretty ingenious. It was also very labor intensive, so I don't think they do that kind of stuff anymore. Okay, but that's soil creep. That's slow movement. A landslide, on the other hand, is any slow to rapid downhill movement of materials. And that would be, right now you're hearing about in California and other places out there, how terrible the droughts are and the wildfires, okay, caused by the drought. Well, along come late winter, early spring, if they start having rains and all the vegetation has been burned off, then they'll have landslides. So it's a pretty bad situation out there, because the more that they have fires, the more likely they'll have landslides later. It's a slow to rapid downhill movement of materials. Usually you can see and sense that a landslide is happening. You'll hear the rumbling. You'll see the soil moving downhill. And sometimes it's more than soil. It may be rocks and boulders and gravel and other things. Slow to rapid movement that you can tell something's going downhill. Soil creep, it's always happening. Gravity is causing both of these. Gravity's making it happen rapidly here, slowly here. Now, what I was trying to describe in California, when they get a lot of moisture in that soil, their soils have a type of clay that swells. All clays swell when they wet, okay? But this one really swells, and when it does, it loses its strength, and when it loses its strength, it's more likely to be pulled downhill. And that's sometimes called mudslides, but that's a type of a landslide. Now, what are the causes? The major of the causes for erosion is water. The most important of the gravitational erosion processes is running water. Because guess where water runs? Downhill. Always is running downhill because gravity's pulling it downhill. You'll never see water running uphill. Not naturally, okay? It runs downhill, okay? And that running water is essential for plant growth. It also exacerbates erosion, okay? Now they mention here 3 stream transport mechanisms. To me, they're jumping the gun just a little bit. Let's back up and give 2 major mechanisms of erosion. First is detachment. Soils tend to hang together. Not super tightly, not as tight as a rock would be, but they tend to hang together. That's called the soil structure. What you have to do before you have erosion is to break that structure apart. That process is called detachment, okay? Detachment. And then once you've detached the soil, then you can transport it. Now, an example of that, I don't know, I can remember when I was younger, my family used to uh, go every summer up to North Carolina and see the rest of the family. Ours was the only part of the family that had moved down to Georgia, so we would go to North Carolina and visit with the grandparents and the aunts and uncles and those kind of people, cousins and stuff. And I can remember in the late summertime is usually when we did it. Every now and then you'd hit a thunderstorm would be happening. And you would be driving along and you might notice the clouds are looking sort of bad, but boy, when that first raindrop fell, it looked like it was splat on the window that big, you know. And that's because it finally came down. We'll talk about that in the weather chapter, what causes that rain to do that. Well, that raindrop, big old raindrop, coming from a high distance, has an enormous amount of what they call kinetic energy. Kinetic energy is 1/2 the mass times the velocity squared. So if it's coming from a high distance, that means it has a lot of velocity, and if it's a big old raindrop, it has a lot of mass, so it has a lot of energy, kinetic energy, that's going to, when it hits the ground, splats it up, and you've seen places where it happened, that raindrop fell, it looks like a little crater there, because it detached the soil particles. And once they were detached, more rain comes and washes them away. That's transport. The washing away is transport. This jumps right into the transport. 3 stream transport mechanisms. The first, if you remember, earlier in this chapter, we talked about chemical processes. One of the major chemical processes is hydration. Hydration is dissolving materials. So water dissolves materials. So that transport mechanism is the water dissolves some of the soil materials. Remember we said here, previous slide to that. This one, it said the salts that are in the soil, when the water hits, it dissolves some of those salts and other things as well. But those salts, which are often your nutrients, it dissolves them, there it goes, downhill, away from the field, the yard, wherever you want to do it. Okay? Number 2 is suspended materials. Now, what's the difference between a solution and a suspension? A solution, if you held it up in a clear glass, you can see through it. A solution, the dissolved materials, the water has gotten in between the various particles and you don't see the particles anymore. Think sugar in tea. That's dissolved, especially if you put it in when it's hot. Salt in water, if you're gargling or something, or the salt water of the Gulf of Mexico or something like that. You don't see the salts in it, but you can sure taste the salts in it. That's because those materials are dissolved. If they're suspended materials, that makes it look cloudy. That makes it opaque, or mostly. One example of that would be milk. You can't see through milk. You can see through tea probably pretty much, but you can't see through milk. Why? Milk has calcium particles suspended in it. It has a little bit of fat suspended in it, unless it's fat-free milk or skim milk, but it has things suspended in it that makes it hard to see through. This next picture here, you can see water is running downhill this way, running downhill that way. Some of this is fairly clear looking water, guarantee you it has dissolved materials in it, but as an aggregate, it's sort of murky looking. That means it has suspended materials in it. What are those suspended materials? Clay particles, silt particles, possibly even sand particles. If the water is running really fast and can carry that sand, it can do it. The third mechanism, yuck, rolling, bouncing, or sliding along a stream bed. The water is going down like you see it here, and it's going so rapidly down that stream bed here and here that it's bouncing some of this suspended material off the bottom, loosening up other material. So in other words, it is doing detachment and transport at the same time. Okay? Now, stream beds evolves over time. Okay? They make that little statement here. We're going to talk about it, and then later we're going to talk about it again in a slightly different way. So if you think it's deja vu all over again, you're almost right. Stream beds evolve over time. And this is getting into stream development. Now, there are some examples in your book. Some of these may be worthwhile, some of them are not. Example 20.1, what is the slope and percentage grade for a mountain road that drops from 2 kilometers in elevation to 1.2 kilometers over a distance of 3 kilometers? Well, what does that have to do with anything? It's just talking about it's going downhill. The math here is pretty straightforward. You can certainly follow it. And example 2.2 is about the same. Example 2.3 is talking about looking at soil creep. They're looking in a graveyard and they're measuring the angle at which some of the tombstones seem to be doing and comparing that with the dates of the tombstone, and sure enough you see that the displacement for the older ones is generally a little bit greater than the ones that are more recent because of soil creep. Again, they sort of just making up a problem. Then they talk about creeping trees, and you can certainly look at that too. That was that picture. It's kind of nebulous there. Okay, so we won't go into that. They do show a river here, or a stream of water, similar to one we saw on our slide, but this is much larger scale. Oh my goodness, look at that. You can tell they've had rain recently. Why? That's not clear water. That's murky water. That has a lot of material suspended in it. Probably has a lot of dissolved material too. Definitely has suspended. Now, it's not moving that rapidly. That came from somewhere further uphill. Okay? Then they get into running water, and they talk about they have some other examples there. Some of that, again, they sort of throw in the examples here. I don't see really that much value. Look at them. You might learn something from them, but we'll leave it like that. Now I'm trying to get to stream development here. Okay? And this will be they show the illustration that we're going to see on page 513. I'm trying to see, yeah, that's pretty much where this is. Okay? Actually 512 is where it's talking about this. Now, like I said earlier, you're going to see this again with different terms on it. Same words here, but talking about something else. Now, hold on just a moment. This morning was quite cool here, but this afternoon has warmed up quite a bit, so I needed to turn on a ceiling fan. All right, sorry about that. Stream development. Early in the process of stream development, your land mass, especially if it was recently uplifted or was sort of flat and level and stuff like this, and you start forming a stream, usually it's a large, what they call gradient. It's coming down at a pretty good angle. And when it comes down, it eats out into a V-shaped valley. Do you remember when we showed the picture early on of the upper Yellowstone Falls, and I pointed out how the sides of the banks of that river just came down in a V-shaped angle? That's what they're talking about. That's a fairly youthful stream development, even though it's been there hundreds of thousands of years probably, but in geologic time, that's pretty recent. Okay, so very little floodplain. And you saw there was no place where water was just hanging around. It was all going downhill pretty fast because of that steep gradient. Now, you have boulders along the sides that are resistant to the stream movement. You have rapids where they go through areas pretty quickly, and you tend to have waterfalls, and you saw that in the upper Yellowstone Falls, River Falls. Now, here is the picture of that. The youthful stream development. The streams are running downhill very quickly. The valleys are pretty much V-shaped all along in every dimension, V-shaped valleys, and your mountains are tended to be pointed and jagged. Okay, very distinct here, and there's no place the water's hanging around. It does a little bit here, but that's because you got three streams coming into the same place. A little bit here because you got two coming in. And you tend to have boulders, rapids, and waterfalls. Now, I can't see for certain a waterfall here, but you could easily imagine one maybe here or somewhere back here. Now, a more mature stream development would now be, over time, those hills have worn down, mechanical weathering or physical weathering, biological weathering, chemical weathering. You've worn off some of the jaggedness of the peaks, you've rounded the hills, and filled in the valleys. The valleys, the breakdown of the rocks up here has filled in the valleys here. And that's why quite often with mature environments, right near rivers, you have very, very rich soils. Really good. Okay? Mississippi River Valley, a lot of really great food has been grown along there. Okay? Out in California, you'll hear them talk about the places, the San Joaquin Valley, the Empire Valley. They're valleys. That's where a lot of the soil has built up recently, fairly recently, coming off the hillsides. Now, the stream gradient is smoothed and lowered. Rather than coming down rapidly, it's still going downhill, but it goes down more slowly. It will get to some places that are floodplains, and there it tends to meander. It doesn't go straight downhill because the slope is so gentle, it sort of wanders around, finding the easiest route and going. It's not in any hurry. That's a mature landscape. Now, the bad news here, you still have a floodplain, which means when you have heavy rains, you tend to, this whole valley would then flood. Well, there's that rich soil that you were talking about growing your crops in. All of a sudden you get heavy rains and your whole crop is wiped out because the water overflows the banks of the river into the floodplain. That's not going to happen up here because you don't have any floodplain. Okay, you just get more erosion up here and it fills in down here. In the old age stream development, now you have a very low gradient. The water just sort of drifts along. Okay, broad, gently sloping valleys, if you have them at all. Most of the valleys have almost disappeared here. What you have is really broad and gentle slopes. What you have is sluggish flow. The water's in no hurry whatsoever, and now you talk about meandering. It's really meandering. But because of that, when you have a heavy rain upstream, now you get huge floods down here. Okay. Now, I did want to point out a feature here they don't mention on the slide, though they showed it. What in the world is this little thing here? That's called a bow lake. And here's what it probably was in the past. In the past, this wandering little stream probably came over here and went back here and joined up here and wasn't even over there. But then something happened over time. You ate out a little more soil here. This may have been more resistant to erosion, and this lake got cut off from the original stream, and that's called a bow lake. Now, I encourage you to go get a map. A map of, say, Mississippi, Louisiana, Texas, anything along a major river, preferably the Mississippi River, and look at a pretty detailed map there, and you're going to see the Mississippi, especially when it gets downstream, it goes like this. It just is all over the place. Every now and then you'll see a bow out here or a bow over here or something where it used to come here and then it quit. Okay, those are your bow lakes. My wife's brother lives, and his family live in Alexandria, Louisiana. That's almost smack in the middle of the state. Okay, but they got them what they call a camp house, you know, out on. I don't know if you're familiar with Louisiana. It's Natchitoches is how you say it. You don't spell it that way at all. It's really an odd spelling. And anyway, it's over near the Cane River. But they're not on the Cane River. They're on the Cane River Lake. Well, the Cane River changed its course and left a lake behind, okay? And they have their place on Cane River Lake, but it's not on the Cane River. So they don't have necessarily flowing water through it. They have, that would be through the Cane River. It's sort of, it's not quite stagnant, but it's coming pretty close to it, okay? Still good enough you can eat the fish from it if you like fish, okay? But that's your old age environment. And just like old age people like me, we move a little more slowly. Take the path of easiest, least resistance, okay? That's what your old age stream development is. All right, there it is again. Upper Yellowstone River Falls. Look at that steep V-shaped gradient there. That's a fairly youthful stream development. Like I said, maybe only been there a few thousand or 10,000 years. And whoa, here comes somebody. Drew's here. Good deal. Okay. Got Drew here. Good deal. Now we're only missing Deja, who I think may have had surgery. Amari. Good, thanks. Good to have you here. And Sancho, we're missing him, and Avius. So glad you made it. Now, Drew, the others have heard this now several times, but I want you to hear it too. We're going to kind of put on the brakes a little bit here. I just realized we have been racing through this course as if there's no tomorrow, okay? I don't think it's the fact this is my last term. I don't think that's it. I think it just, we've had fewer problems. That first term, spring, when we had to leave campus and come, oh my goodness, there were problems. Oh, here comes Sancho. So here's another one coming in. Good, so I'll save and put all this together for both of you. Okay?
Yeah, Mr. Charles, in the spring, man, there was problems every day, man. I just had to drop a class.
Yeah, it was, I mean, I was having problems. I was trying to teach it. My computer died on me twice. My internet went off for more than 2 days, so try to have a virtual class with no internet. That was not fun. My wife had a hotspot. We have pretty weak signal here. Well, she was trying to work off the hotspot, and I was trying to work off the same hotspot. Everything slowed down. It was miserable. Then in the summer, there were still some issues like that popping up. But this fall, at least on Tuesdays and Thursdays, things have been going really rapidly. And I think I just got into the habit of just trying to get as much done as we can every day because you didn't know when it's going to break down. Well, we can slow down a bit here. So for those who've just gotten in, here's what the plans are. We're in chapter 20 today. This is the 7th chapter out of only 9 chapters we're going to do, and we're only at the end of the 5th week. So, whoa, we've been racing too fast here. So what we're going to do is the rest of the day we're going to spend in chapter 20. We're going to take our time, go through it, make sure we hit it well, but we'll probably finish chapter 20 before the day's over. Okay? Even if we finish it before our normal lab time, 3:45, rather than jump into the lab and rush through that too, we're going to take a time out. And I'm going to have a time for you to try to catch up old labs, maybe even old tests. And if you've got all those caught up, if you haven't done your research paper, I think only 2 people have, then I suggest you work on your research paper. So
So, Mr. Charles, that's gonna be like a 30-minute break right there, right?
it's going to be as long as you need it to be. Okay?
Oh, before lab. All right.
No. I mean, we're going to finish this chapter. That may take us into the lab period, or we may finish it before that. However long it takes, we're going to finish the chapter, but then we're going to stop and not do a lab today, except for catching up on past labs.
Okay.
Yeah. Or if you want to, work on your research paper. Or if you have tests that you're behind, try to work on your test. And then next Tuesday, we'll start fresh with chapter 23. Only go for 2.5 hours, stop then, and then do the lab for chapter 20. Okay? Once we do the lab for chapter 20, I'll give you the chapter 20 test. Okay? Then next Thursday, we'll finish chapter 23, probably. I think we will, or at least we'll make good progress on it. And we'll probably do the same thing we do this week. Pause, see if there's anything you need to catch up on, because no reason racing through this when we don't have, so we'll do that. And then the following week, which will be week 7, because this is week 5, next week is week 6, the following week is week 7, then we'll start chapter 24 and stop after 2.5 hours and have the lab for chapter 23. Okay?
You say which chapter this class goes to again? What chapter are we supposed to go to?
We're doing 20 now, then we skip 21 and 22. I would go on and throw one of those in there, except some of you have books that don't even have those chapters in them. So I don't feel that would be fair to you. If you bought a book from the bookstore that only has the 9 chapters we're going to do, then it wouldn't be good to throw in an extra chapter on you. That would not be fair to you. So what we will do is go into, so we got after chapter 20, 23, and 24. That I think was your question. Okay, so then the week 5 we're finishing 20. Week 6 we start 23 and do the lab for 20 and test for 20. And then week 7 we do the lab for chapter 23, start chapter 24, do the lab for 23, and work on chapter 24. And then week 8 we finish up chapter 24, we do the lab for chapter 24, we have the test for chapter 24, and then we have the final exam, and we'll be through. So how does that sound?
Sounds like you got this pretty scheduled out.
Okay, so we've been going breakneck speed up till now, going sort of hold back. We're going to go from being youthful landscape and running downhill as fast as we can. We're going to get into the old age here and slow it down a little bit. Okay. This was the picture of the upper Yellowstone River Falls, and notice how steep this grades is on the side here. That's a V-shaped valley. This is a youthful landscape. Look at how fast the water is running down, not just over the waterfalls, but down here as well. Let me make sure I've got 15 students here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, got it. Okay. Things keep popping up on my screen. I want to make sure someone hasn't gotten booted out and trying to get back in. All right. So this is what we call a youthful landscape. Steep valleys, rapid grade of your stream bed. You have waterfalls, rapids here, rapids down here, waterfall up here. Highly resistant rock here, but it's still been eaten away. At one time, this rock went all the way across. But slowly, the movement of the water, that would be physical weathering. The dissolving of the water by the water, that would be chemical weathering, and perhaps some acidification of the water, that could be chemical weathering as well. It's worn that down and worn it down. This falls used to be up here somewhere. Okay, slowly over time it's wearing and wearing it down. Okay, so that's a useful landscape. Let's see if I can get the slide to progress. I thought they would have there a not so useful landscape. Let's see, I think in the book they show that. No, they don't. In the book, actually, they have another falls there. I think this is the lower Yellowstone Falls. The one that you saw in the slide set there was upper. I think that's a picture of the lower Yellowstone River Falls. Again, very V-shaped valleys, so that's again a useful landscape. Okay, now it does slow down a little bit below there, because not too far below that it runs into Yellowstone Lake, so it really does slow down some there. Okay, now let's move on to deltas. Okay, now what in the world is a delta? It's basically a deposit of sediment. Now they say at the mouth of a river or stream, but it doesn't have to be. If you go back to this picture here, these are sediments in here too. The mouth may be down here somewhere, but you get sediments up here too. These are also called delta areas, where sediment has fallen out. But most of the time we talk about a delta as being near the mouth of the river. And that's what they're talking about here. Deposits of the sediment at the mouth of a river or a stream. Okay? And this would be sediments of a stream. These would be sediments of one of these two streams, or both of them. But you also get it at the mouth of the river as well. So yeah, that showed both of them. But it's just sort of hidden. Okay? Now, the stream flow dissipates into either an ocean, a lake, or maybe the Gulf of Mexico or someplace like that. The flow sort of comes to an end. Just like I said, even in this rapid, the one I showed you here, rapidly flowing lower Yellowstone Falls, shortly below here, it's going to slow down and go into the Yellowstone Lake Yellowstone. Okay, so at that point, the erosive and sediment carrying ability of the soil, of the water, is lost, because it's that rapid movement downhill that gives it the energy to carry more of your soil materials down, cause more erosion, carry more sediment. But as it slows down, it loses that mechanical energy, that kinetic energy, and slows down, and now it can't carry as much stuff. First, your gravel will fall out, then your sand will fall out, and ultimately the clays will even settle out. And you'll see that sometimes, especially at a place where, say, a river bends around. On the inside, that's where the water is moving more slowly. On the outside, it's moving faster. Well, the gravel and sand will fall out on the outside. The clay and the mud will fall out on the inside because it's moving more slowly. So that's what a delta is. Here is a picture of a delta, and this is very similar to the one you got in your book. Not quite. The one in the book is a bigger scale picture than this. But you see, I will almost guarantee you, not knowing exactly where this is or anything, I think that just about everything you see, now is that someone trying to come in? Let me see. Nope. It seemed like we got the same people we had before. Okay. Just about everything you see here is sediment, thing that's been dropped off by a river. More than likely, this river here originally was somewhere way back there, and your bay, your gulf, whatever this is here, was way back there. This is soil that's been brought downstream by the rapidly moving water, and then as the water slows down, it drops out the soil. These are deltas. This whole area here is called a delta. Now here was the original landmass here. This is a pictorial drawing. The river came down here and then sort of stopped, and this was the original riverbank right here, and whatever you call it, bay or lake. They call it a lake. Okay, it came right up to here. But over time, this water coming from here, bringing the soil from upstream, deposited here and here and here, and over time keeps putting deposit on top of deposit on top of deposit on top of deposit, and these form your deltas. And the water sort of meanders through that, and there was a lake that used to go through here, got cut off. That's happening. Now, I'm going to show you this picture. I don't know for certain where this is. I have a feeling I know. It's got so much cloudiness to it, I can't tell for sure, but I wonder if that's not Louisiana. Take a look at Louisiana on a map. What is it that goes through Louisiana? The Mississippi River. The Mississippi River started way up there in Minnesota. The Missouri River started somewhere way over there, probably in possibly North or South Dakota, maybe Montana, probably Montana, somewhere over there. And the two of them came together, and then the Tennessee River came into it, the Ohio River came into it, covering huge areas of the U.S. Let me make sure nobody's coming in. I don't know what this noise is. I don't see anyone. Huge areas, and it's picking up soil. It's picking up erosive soil all the way, bringing down, and then it slows down and dumps into the Gulf of Mexico. And if you look at Louisiana, it sticks out into the Gulf of Mexico. Why? Because all that is delta area. That is soil that was brought down hundreds of years ago, thousands of years ago, 10,000s of years ago. Most of the state of Louisiana, or a lot of that near the base, is delta area. Now, where I was talking about my brother-in-law lives, that's probably original soil. Okay, that was always land, or most of the time land. Okay, like this was. Okay, but the rest of that, awful lot of New Orleans. Some of New Orleans is actually below sea level, folks. That's why it got flooded so badly with Katrina. What do they call it? The levees broke and water came flooding into it. Ninth Ward got it really bad. Okay? But all that, when you look at that map of the Gulf of Mexico, you see Louisiana sticking out there. That's pretty much all delta area. All delta. Okay. Where the river carrying sediment started losing its ability to carry it any further, it dropped it off. Okay. Let's see if we can get it to advance. All right. So the number one cause for erosion, well, all the cause for erosion, not all, most of the erosion is caused by gravity. Gravity pulling water downhill, that's the number one. Number two, though, and this is not minor, these are glaciers. Believe it or not, glaciers are moving. They're great big sheets of ice, masses of ice on land, and they move. Guess what? Gravity pulls them downhill. You'll never notice them moving. They're moving so incredibly slowly, but they're always moving downhill. Always. They form from snow that is accumulated over a number of years. Can be as few as 5 years. That's if you had heavy snowfall 5 years in a row, filling up an area, up in the mountains, say, and that can form a glacier. Other glaciers are up to 3,500 years old, okay? Accumulated over 3,500. That's 3.5 millennia. Okay, that's we're in year 2000. This would be 1500 BC was when that glacier started filling up with snow. Okay, long time ago. They basically classify glaciers two different ways. Now, this first way, this is not the best name for it, but they call them alpine glaciers. The reason they call them that, they were named after the Alps, the mountains, Alps mountains in Europe, the major mountain range in Europe are the Alps. There are many other important ones there, but the Alps are the biggest. They cover the most number of countries. They call them alpine glaciers. They form at very high elevation, where of course the snow falls at high elevations, and then they flow through the valleys, and the better name for them would be valley glaciers, because you have valley glaciers in Europe, in Asia, in Africa, in North America, in South America, anywhere there's a valley. However, to call them an alpine glacier, that's what they call them, but they're nowhere near the Alps. Okay, Europe, that's in Europe, but not in Asia and Africa and North and South America. Those would not be alpine glaciers, so they call them that. The better name is valley glaciers. Okay, this is a picture of a valley glacier. See, the mountain peak is sticking up here and here. There was a valley in here, there still is, but now it's not completely, but largely filled with, it's on top is snow, but underneath that is ice. And that ice, believe it or not, is always, just like a river would be in that valley, moving downhill. It's just moving incredibly slowly. Okay, so that's the first time, the valley glaciers. The second kind are called the continental glaciers. They cover large areas of a continent, and today they're mostly in Greenland and Antarctica. Antarctica is almost completely covered in what they call continental glaciers. There are a few mountain ranges, I think, near the center of Greenland. There may be more some other places too, but most of the flat land is covered with glaciers. Those are continental glaciers. Greenland, much flat land, is covered with glacier. There's one place up in, I can't remember if it's British Columbia. I think it's British Columbia. It might be Alberta, Canada, that is called the Columbia Ice Fields. And that has to be what they call a continental glacier. My wife's family used to take pretty major vacations about every 3, 4, 5 years, to save up, so they could go on a big one. And we made a couple up in Canada in the summertime, really nice and cool to get away up there. And one time we went as far over, I think we were in British Columbia by the time we got there, to the Columbia Ice Fields. The city up there is Jasper, just like Jasper, Alabama, but this is not Jasper, Alabama. And somewhere even further north of that, we drove up, we drove up to an area, and there just the whole flat area was covered with the Columbia ice fields. That had to be considered a continental glacier. So they don't mention it here, but Canada, I'm pretty sure, has at least one, maybe more than one. Now, the really sad news there. Now, that glacier had been there long before we ever found it. When I say we, European settlers ever found it. But when they first discovered it, though it had been there a long time before that, the locals knew about it, everybody knew about it, but they just discovered it. Someone drove a stake in the ground at what they call the tongue of the glacier, the very end of that glacier. You could see the stake, you couldn't see the glacier. We had to walk for about 1.5 miles, and finally we found the glacier. It had retreated that much. We're talking global warming here, people. Okay. Kendra, now was she here before? I think she was. So she must have either had to leave or gotten booted out. Yeah, I already had her here. Okay, welcome back. but because it was fairly flat, it took a long, but man, and that was over just the course of about a century and a half, about 150 years, maybe a little bit closer to 200 years, it had retreated that much. Okay? Don't let them fool you. We've been losing this a long time. Okay. But that's a valley glacier there. Now, why are we talking about these under erosion? Because glaciers do erode soil. They wear it down. They erode mountains. They erode rocks. They erode everything. 3 mechanisms they do it. Now let's think about that. What I was talking about before, the tongue of the glacier. Let's just imagine somewhere downstream here, we went to where the glacier, where you might say begins or ends. I would say ends. It begins somewhere way up there, ends somewhere here, finally getting warm enough that it's not sustaining it anymore. The front of that glacier acts like a big bulldozer, okay? And that's the first mechanism. It forms deposits ahead of it, pushing rocks, pushing gravel, pushing sand, pushing soil in front of it, like a bulldozer does as it's doing. Those deposits are called moraines. Now, you probably heard, not just talking about the silly movies, but you've probably heard that in the past we had what they called ice ages. There were at least 4 major ice ages that we know about. And in those times, the glaciers pushed further in the northern hemisphere, further and further and further south as it got colder and colder and colder. But at some point it reversed and started warming up, and the glacier started retreating. Well, the end of that glacier, where it had bulldozed or pushed up those deposits called moraines up to a certain point before it finally started retreating, those often formed like dams that formed lakes behind there, and those are often called moraine lakes. And when we were up in Canada, I think it was that same trip, it was further south, I don't remember exactly where it was, it seems like maybe that was in Alberta, Canada. We went to a place called Moraine Lake, and that had been formed by some glacier, and that was a valley glacier like this one here, had pushed down, I mean it had pushed down boulders the size of 2 or 3 story buildings, plus lots of other stuff, you know, soils and sands and silts and all sorts of things packed together before it started retreating. Okay, and then where it retreated, it blocked off this end, say, of the valley with that stuff it had bulldozed, and then as it melted, it filled in a lake, a beautiful, beautiful lake, and that was called Moraine Lake. So that's the deposits, the bulldozed deposits of the solid materials are the moraines. The lake behind that was called the Moraine Lake. So that's the first mechanism that glaciers do. They push the soil and the rock and the boulders and gravel and everything ahead of it, and then if they finally start retreating, that's left there as a moraine. The second way they erode soil is by abrasion. Okay? Now, if you think about this, you have a valley down here, solid earth valley down here, and all that ice is packed on top of it, and packed and packed and packed and packed on top of it. And that's heavy. I mean, who knows how deep this goes? That side of the mountain keeps going down like this. This one goes down like this. That may be several hundred feet, you know, before you get to the bottom of it. That's a lot of weight, an enormous amount of weight. Okay? And the valley is not smooth. It may be very rough and rocky. The glacier is not smooth. It's heavy. And as it moves along, remember, gravity's pulling it downhill very slowly. as it does, it abrades that rock that's underneath. And that's what produces the powdery, silt-sized rock flour. Remember, I said we don't have that much silt down here. They have it up in the Midwest because during some of the ice ages, those glaciers, continental glaciers, pushed their way down, pushing ahead of soils, carrying soils with it, grinding soils into that silt-sized rock flour. Remember, I said no grittiness to a silt at all. It's like flour or powder, okay? That's what it produced. And those soils do have a great amount of silt in them. And also out west, where you have the tall mountains and those valley glaciers left. So out there, they could talk about loams being a good mixture of sand, silt, and clay with a lot of humus. Well, they had more silt than we do, okay? We have mostly sands and clays, so we don't have that much silt. Well, that's where it comes from, largely from the abrasion of glaciers. Now, let's do a time out here and think about this. I wish we were in class so I could show you a globe. The ice ages that I've mentioned, the glaciers came, continental glaciers came down from Canada very slowly. It got colder and colder, the glaciers got deeper and deeper, pushing their way, grinding their way south always. This is in the northern hemisphere, coming south and grinding that good rich rock that was up there in Canada, grinding it into soil, and ultimately brought it down to our Midwest. Think Illinois, Iowa, Nebraska, Kansas, parts of Colorado. Bring it in there. Some of that has some of the greatest soils on the planet. Where did it come from? Canada, okay? The glaciers ground it down, hauled it down there, and then when they finally melted, they melted, leaving the residue. Thank you, Canada, for sending us such. There are no better soils on the planet than you'll find Illinois, Iowa, Nebraska, Kansas, some of those places. Fantastic, deep, thick, rich soils. Wonderful soils for growing some of the best crops anywhere. Okay? So there's abrasion. Bulldozing, pushing it ahead, abrasing it, grinding it into a rock flour underneath. And then the other way the glaciers erode. Remember all that pressure that you have? Ice on ice on ice, snow on ice on, and so now, I don't know if you realize this, but when you add, okay, let me back up and ask this. Have any of you ever ice skated? Anybody? I've tried it a few times. It's miserable. My ankles were not built for ice skating. I don't know how.
I just seem to just be standing there and walking. I couldn't glide.
Right, okay. And the reason they can glide, though, is that thin, narrow little blade, all the pressure, and what is pressure? Force per unit area. What's the force? It's your weight. Area is how thin that blade is. It's a very small area, so you have a lot of pressure right there. The reason they could glide, okay, I never could slide much either, is because all that pressure on the ice, it actually melts the ice right ahead of it. And then as you go through it, it refreezes because the pressure's gone. Well, guess what? The glaciers do that too. All that pressure from all that weight above melts it right down at the bottom, but then it gets colder and refreezes. Well, what does it do? It refreezes around gravel, around sand, around boulders, around all sorts of material there, and they get frozen into the bottom of that glacier, and that's moving downhill. That's called plucking. The glacier water freezes into surrounding rocks, pulls it along, and basically you got a big piece of sandpaper. That's what's doing the abrasion then. You're plucking and carrying with you that gravel, those boulders, that sand, whatever it is, pulling it along. So there's the other mechanism that it erodes the soil. Bulldozes ahead, grinds it underneath, plucks it, and carries it downstream. Boy, glacier can do a lot. They take their time about it. They move very, very slowly. But look, some of them have been around 3,500 years. They can take their time. They have plenty of time to do that. Now, this shows a landform before a glacier. Yeah, sort of rounded peaks. There's been some erosion, water erosion and stuff like this. Things have rounded. You have some V-shaped valleys here. It's a mixture between a mature landscape and a new landscape. But then you get glaciers coming down in it. The glacier is going to eat out U-shaped valleys, and when it does, it leaves jagged regions in between. So say you have a glacier coming down this one, maybe a smaller glacier coming down here and here. Well, the regions in between get eaten out on both sides, leaving you these jagged peaks. And when you have those jagged peaks, those are called horns. The jagged ridges that you have are called, I don't know how to pronounce it, I think it's arêtes. And sometimes the glacier would have left a circular thing behind it. These are called cirques. I think you pronounce it as if it's a A there, cirque. Okay? In some of those cirques, they call them rock basin lakes. Okay? And they may be downstream one from another. That's another thing we did when we were hiking in Alberta, Canada. We were at a place, I'm pretty sure it was Lake Louise. Beautiful, beautiful lake. Way somewhere up there. Probably at one time had been a glacier lake. Probably somewhere south of there you would find a moraine that had been pushed down and that dammed up the lake. And we went hiking through the woods, and we had heard, and this is what drove my wife's family, and I'm very much a part of it. We had heard this one place up there, and it was quite a ways up there, had the very best chocolate cake you can imagine. So we decided to take that hike. That sounded like it was worth it to us. So we hiked up, and sure enough, we ran into some of these rock basin lakes here. Mirror Lake was one of them, and we'd walk going up and stuff, then find another lake. And we finally got to that place where supposedly the best chocolate cake ever could be found. And boy, were we hungry by then. And we went in and we asked about it. They said, oh, no, that's another 2.5 miles further north. We decided that was enough. What do you have? Well, they had some pretty good pastries, but it wasn't that good chocolate cake we had been looking forward to. But we weren't about to go another 2.5 miles to try to find that chocolate. No, it may have been 2.5 hours. I don't remember. We decided we're going back down. Okay, so you found these rock basin lakes left over by the glaciers where they paused and possibly bulldozed up a dam ahead of them, goodness, I've lost the word now, moraine in front of it, and left a beautiful lake behind. All right, and notice here you have U-shaped valleys here. They were sort of V-shaped before. Now the glacier ate them out on all sides and made a U-shaped valley. Sometimes they had what they call hanging valley. That's what this is, where a less heavy glacier stopped here, ran into this one being heavier, went deeper. Here you probably have some pretty nice waterfalls. Okay, so those are some of the land features left over by glacier erosion. Pretty bland looking beforehand, very remarkable afterwards. And you can see how the glacier influenced that. All right, now the third type of erosion, you have water erosion, you have ice erosion, that's glacier. Now we have wind erosion. This one's not caused by gravity. Earlier they made it sound like all of them were. Wind erosion is not caused by gravity. Wind erosion is caused by the wind. And the wind is caused by several different factors, and we'll talk about that a little in this chapter, but more in a later chapter. Now the wind, if you think about the kinetic energy, 1/2 mv squared, the mass of air is very, very, very light. The mass of water, a bit heavier. All that ice, really heavy. But of course, in a glacier, the velocity is very slow. In water, the velocity can be pretty fast, and so can the mass. But in wind, the mass is just so low. It's a lot less energy, so considerably less efficient at eroding soils than water or ice is. Water is very efficient. Ice is very slow, but incredibly efficient. But in wind, now here we have some of those same terms we talked about before. Two major processes. Now I gave these two before, but I used detachment and transport. With wind, they call it abrasion. Now that's very similar to what we had back here, abrasion. That's rubbing something against something else. Well, here wind abrades as well, and they call that natural sandblasting. I don't know if you've ever seen a building, say downtown or something, that had gotten really dark and dingy looking because lichens and molds and mildew and everything else was growing on it, and they come in and sandblast it and make it nice and pretty and light colored, again, that's sandblasting, wearing off things that surface coating. Well, when wind carries with it little particles and bumps against rock formations, it sandblasts and breaks off that's the abrasion, breaking off of material because of the kinetic energy of those particles in the wind. Now this produces what they call, I don't know if you're familiar with the term artifacts. An artifact is something left over after an event. Because this is a wind event, they call it a ventifact. Ventilation, vent, meaning wind, ventifacts. Remember that arch-shaped rock formation that we had very early in the chapter? That was mostly a ventifact. It made by the blowing of winds. Because there wasn't water going through that, that was wind. That was a ventifact. The shape can depend on the prevailing winds. Now here's just a generalization. It's not going to show you anything as pretty as that was. But if you have prevailing, and mostly here in the U.S., we have prevailing westerly winds coming from the west. And if they're constantly coming from the west, and most of them are, they come, and if they are carrying little pieces of sand or grit or something with them, they'll hit the rock and wear it down. Wear it down just a little bit. Okay? That's abrasion, natural sandblasting. Now, if you had wind changing direction on you and start coming from this side, then you can start having that happen. That typically doesn't happen. We have prevailing westerly winds. When I was out in California in the Navy, a few times I had to drive up to Sacramento. I was in the San Francisco area, had to drive up to Sacramento. Now out in San Francisco, the wind's always, always, always blowing in off the Pacific Ocean. That kept San Francisco sort of pollution free mostly. It also kept it sort of chilly mostly, especially in the summertime. It sort of moderated your temperature. Winds always coming from the west. And when I drove up that interstate, I don't remember which number it was, 70 maybe, that went up from San Francisco to Sacramento, they had tried to plant trees in the median, and all the trees were leaning this way. Now that wasn't because of soil creep, that's because the wind was just always blowing from the west, making them lean toward the east. Okay? Well, if that's doing that to trees, if there were any rocks in the way, it's doing it to the rocks as well. Okay? The shape depends on the prevailing winds. So abrasion is the natural sandblasting, breaking away little particles. Deflation is then when the wind picks it up and carries it off. Okay? Like it may have picked up a bit of gravel here, made it abrade here, and then the piece it knocked off get carried over the top. So that is the transport. Wind transport is called deflation. Okay, why they use a different word, I don't know. The loose material is picked up and carried away by the wind. Now, they do have in areas, now you think of this as in beach type areas, you have sand dunes. But you can have sand dunes anywhere where wind has carried soil and dropped it off. Okay? Certainly that happens near the ocean. The ocean pushes sand up and the wind carries it down and make the dunes. Low mounds or ridge of sand or other sediment. Now, when I was living in Nebraska, I lived there about 5 years when I was doing my graduate work. And I was over in Lincoln, Nebraska just about the whole time. But I had a friend who lived out in what they called the Sand Hills. And I thought, why in the world would they call them that? And she invited me to go out to visit her mom out in the Sand Hills. And my goodness, those were hills. I mean, great, big, massive hills. They were rounded, they were dunes. At some time in the past, it had to have been an enormous wind that carried it over the Rocky Mountains and stuff, and then lost steam and dropped off the sand there. Incredible, those sand hills of Nebraska. Unlike this flat type area you found in eastern Nebraska, out in western Nebraska you had those. Now someone I think must have just had to leave because I'm down to 4. Oh no, Jackson's trying to come in. Sorry, I hope you haven't been there long. Have you? Well, no, he's not in yet. He's joining now. I think I already had Jackson here, right? Yeah, I had him. All right. So, that is your dunes. Wind-blown deposits dropped out like you have sand dunes by the seashore. Those are partially formed by water dropping off sand, but in places like Nebraska or other places, you have those dunes. Now, there's also, that's more the sandy, heavier type materials. The loess, and this is pronounced like it's L-U-S-S, but it's loess, is fine-grained dust deposited over a large area, not in big piles, but in a large area. Now, I can't read this part of the chapter without thinking back historically. I wasn't there, but believe me, okay? But thinking back to what I've read about the Dust Bowl. Any of you know what I'm talking about? Way back when we were first, say again?
The Dust Bowl is when the storm came through, I guess, and all the dust came up and the people had to end up moving out.
Yeah, yeah, you're a good synopsis right there. Let me give you a little bit background history on it. When we were first settling the U.S., we filled up the East Coast and people started gradually moving further west. A lot of the draw was the Pacific, but that's way out there. So people started moving west, and when they were moving west, some of them really got tired of moving, and they found there in the middle of the country great flat areas, the Great Plains they called it. Hardly any trees there, just incredibly dense grass, and that's where the buffalo roamed, and that's what they ate on, the incredible strong grass. Well, at that time, it just happened to be a time when we were having above average rainfall in that area. Now, they didn't know this, that the first time they'd ever been there. They thought that was common, that they had plenty of rainfall, deep, thick soil. Remember all that soil coming down out of Canada? They didn't know that either, but really rich soil, really rich grass there, supported these huge herds of buffalo. Hey, why move to San Francisco? Why move further west? I'm tired of traveling. Let's stop and go here. So they did. In fact, there were efforts to make people homestead in those areas. And they got busy. Now, there weren't any trees, remember that? Not many trees at all, so there wasn't much to build houses out of. So what they did, they would cut up, remember I said these grasses, really, really thick grasses, they had deep, deep root systems because that soil was so rich. So they would dig up just big old bricks, probably, I'm just guessing, 6 to 8 inches thick and probably close to 1 foot square chunks of this sod, they called it. It was the soil being held together by those strong, strong old roots. They would dig up the sod and use that as bricks to build their houses. Now, those houses were called the soddies, the old soddies, S-O-D-D-I-E-S. Never hear that term anymore, but that's what they were called. And my friend's mother who lived out there, she lived in an old soddy. Now, it had been upgraded. They had put a false front on it, I don't know, vinyl or brick or something, and they put sheetrock on the inside. So you couldn't tell it was a soddy until you looked at the windowsills. They were that thick. I mean, they were a foot or more thick. Okay, that's why I thought that's about the size of the bricks they had. They were also, remember, they were pretty, anyone ever watched the Little House on the Prairie? It was an old television show, series and stuff. Boy, they had disasters every week. But that was really fairly true. Not every week, but they had a lot of tough times out there. Well, all sorts of things happening. Well, that really was, life was hard out there. So it got really cold in the wintertime. And their soddies, that thick of soil particles, soil material, that was great insulation. They didn't know they were building well insulated houses, but that was fantastic insulation. So my friend's mom, she had a nice, comfortable house, even though it got really, really cold out there in the sand hills. So anyway, so we came along, dug up that sod, built the houses with them, or threw it away, or whatever they did with it to get rid of all that heavy grass. That grass was in their way. And remember, the topsoil went down for feet, so they got rid of the grass covering, and they started planting their corn. I don't know if they had soybeans back there, planting their soybeans, planting whatever crops they wanted to do. They took away the natural cover, the grass, that covered and really held that soil together, and planted crops. And they were very successful for the first decade or two. But then the weather changed. Went back to normal, though they didn't know this was normal, and all of a sudden crops were failing like crazy. No rainfall like they were used to having. And then here came the winds. Well, they had taken all the grass up, built their houses, had thrown it away, burned it, whatever they did with it, left bare soil where they put their crops. The crops failed. Nothing was there to keep the sand in place. Here came the winds. Wind, wind, wind. And that's what created the Dust Bowl. And people lost, like you said, everything. It was awful. Okay? Now, some of that dust, loess, L-O-E-S-S, made its way as far as Pennsylvania. Philadelphia, Pennsylvania had dust deposits that came out of probably Iowa, Kansas, Nebraska, those kind of areas. It was incredible. It was a major disaster, mostly of man's own making. Okay? Lots of people bit the bullet pretty badly there. So that's what I think of when I think of windblown deposits, loess, the dust bowls. Now, they have those all the time. I have a niece, my older brother's oldest daughter, is married to a guy who works for Honeywell, and they're right now in Dubai. And they talk about, that's in the Persian Gulf area, and they talk about the dust storms, the wind storms they have out there. And I mean, and when we were there, I wasn't there, but when the U.S. was there in the, whatever they called it, the the wars there, rock wars and things like this, when those dust storms would come, equipment would just get completely corroded with all that dust being blown into it. Places you weren't supposed to have dust, and sand. They call them sandstorm storms out there, and they're awful. They'll take the skin off your face, they say. It was just miserable. So that's wind erosion. I gotta click on my slide before I can advance. Now we get into what they call, and by the way, let me see if I'm covering all the good illustrations here. This, remember we saw before a valley glacier. Here's the end of a valley glacier. Okay, it got to here and it started melting. So everything is running downhill, but behind there is the valley glacier. Now this, you don't have a really good idea, but that's probably several feet thick. I would say 15 or 20 feet of ice you see on the edge there. And probably back there is 50 or 60, 100 feet deep. That's the end of a valley glacier there. All we saw was the middle of it before. Okay. This book likes to put these little things in there. I think this was pretty thing. As unchanging as the hills, that's a very poetic sounding statement. But guess what? The hills, they are always a changing. So they just made a deal about that. Now, before we go any further, here is, now this I think belongs several pages before this. This is talking about acid rain. And I think we brought this up when we were talking about chemical weathering. All rainfall is slightly acid. Not much, but a little bit. But when you have a lot of industrial pollution, you can have a lot more, a lower pH. And this table takes you through some of the pHs of common materials, or maybe not so common. There are some discussion questions here. These may lead you to a paper topic. Now this can't be the source for your paper. It can be the source of ideas for the paper. But let's look at some of those pHs. This measures how much acidity. The lower the number, the more acidity you have. Hydrochloric acid is just about the most acidic thing you got. Its pH is 0. Okay. Your stomach acid is next to that. Believe it or not, you have within your stomach some of the strongest acid on the planet. That's what digests your food for you. That's around 1.6 to 1.8 pH. Now, I don't know if you've ever known anybody, and maybe you yourself, I hope not, but if known anyone who had an ulcer. The reason they have an ulcer, they have very, very high, all of us have very strong acids in our stomach, but if the lining of the stomach, which has to be one of the most incredible materials on the planet, the lining of your stomach that can stand that acid and not be burned up, if that lining gets damaged or thin and it eats into the actual tissue, that's what an ulcer is. And I've heard they hurt like crazy because you've got that kind of acid, 1.6 to 1.8 pH, eating into flesh. That's what makes them so bad. Of course, what they do, they treat them by giving people very alkaline things like not Pepto-Bismol, but Kaopectate or things like this that are trying to neutralize that acid. But that acid is natural in there. So you do that, now you don't digest your food as well. It's a mess. Okay? Lemon juice. Any of you like to chew on the lemon after it's done? 2.2 to 2.4. Your dentist is not going to be happy if you're chewing on that. That can eat away enamel. Vinegar. Anyone like to sort of drink the vinegar when you're eating your pickles or whatever? 2.4 to 3.4. Very acid. Now here is the surprising thing. Carbonated soft drinks. Now this one happens to be not carbonated. This is phosphoric acid. In a lot of your darker soft drinks will be that. They don't give that one, but it's probably around the same pH, 2.0 to 2.4. Hey, that's really acid. Not a good idea to drink too much of those things. Does it do any good to your teeth? Does it do any good to your stomach, your esophagus, anything there? And yet we drink a lot of it. Now my wife really likes this sparkling water that you can get. Doesn't have the sugar in it, and that's good, but still has the acid because that sparkling water is carbonation, carbonic acid. Remember that term from before? Then you get up in the grapefruit, which you think is pretty acid, but lemon is way more acid, vinegar is way more acid, but grapefruit is less acid in general, or right in the middle of your carbonated soft drinks. You wouldn't think that, but it is. Grapefruit 3.0 to 3.2. Oranges 3.2 to 3.6. Then you hit your acid rain. That's 4.0 to 5.5. That's not natural. It's not natural for rain to be that acid. What causes that? Industrialization, where you're putting a lot of carbon dioxide into the air, like steel plants, power plants, things like this are burning coal, burning natural gas, burning anything. Cars, are burning fuel. They're putting sulfur dioxide in the air. They're putting carbon dioxide into the air, putting some nitrogen oxide into the air. Water combines with sulfur dioxide, you get sulfuric acid. Water combines with carbon dioxide, you get carbonic acid, just like in your soft drinks. Water combines with nitrogen dioxide, you can get nitric acid, a very strong acid. That's where acid rain comes from. Our pollution has done that. Now, we've gotten far better at cleaning ours up, but there was a time before the EPA, before the Clean Air Act, which was sometime, I think, in the 60s. I'm not absolutely certain on that, but I believe it was, that there were some areas, you remember Pittsburgh is very industrialized, a lot of the Northeast is very industrialized. Wherever the prevalent winds would come from that, and the rains would come from that, some of the forests were being denuded. All their leaves killed, and trees dying, because the water, acid rain, was way too acid. Over in Europe, Germany had some very large industrial areas. Russia had a lot. Downstream, downwind from that, they had huge areas of beautiful forested areas killed because of acid rain. Okay, so it's nothing to mess with. Tomatoes, 4.2 to 4.4 pH. Potatoes, getting less acid all the time, 5.7 to 5.8. Natural rainwater, 5.6 to 6.2. That we're used to. That's common. That's okay. Nature is built around that. Not built around 4.0 to 5.5. Not. That's too acid. Then milk, and people who have ulcers will drink a lot of milk. That's not quite alkaline yet, but it's close to it. But that's 6.3 to 6.7. And then pure water is pure water, which you very seldom have. It's exactly 7.0. Now, on the alkaline end, they didn't show that here. That would be things like liming agents that have calcium hydroxide, sodium hydroxide, any of your hydroxides. That's going to be higher pH, like 8s and 9s and things like this. Those don't occur that frequently in nature. So that's a good little blurb there. I probably spent too much time on it. They also talk about dune angles. These from, remember, out in Arizona. I bet you they do have sand dunes out there, and you can follow through with that. Now, before we get into development of landscapes, across the page from the acid rain blurb is a blurb on here's the person behind the science this time, and this guy is John Wesley Powell. Okay, and it says 1834 to 1902. So from early in the 18th century, lived through the war between the states in that time just into the 20th century. Now, looking at him there, he's the first sentence here. John Wesley Powell was the most romantic figure in the 19th century U.S. geology. Okay, wow. If he's a romantic figure, yeah, wow, they were a pretty dull group. And I don't know, I shouldn't say that. Anyway, he's a potential paper topic. If you read more about him, you'll see some other names being mentioned here, other concepts being mentioned: U.S. Geological Service, Clarence Dunton, W.H. Holmes, Grove Carl Gilbert. You'll see a lot of potential paper topics there. If you haven't landed on one, check these out. People behind the science. This cannot be the source for your material. It can be the source of ideas for your paper, but it can't be the source of your paper. Get your ideas from here, get your sources from somewhere else. All right, finally ready for 20.5, development of landscapes. Now, this is where you're going to see some repetition. Let's start with the concept of landforms. Okay? Landscapes are made up of landforms. These are the Earth's surface features. Okay? Now, I live in an area called Forest Park. We're just below Red Mountain. Red Mountain's just to the south of us. So Red Mountain would be our major landform here. As you go north of us here, it sort of flattens out. It's not quite as hilly there as it is east-west and behind us. Okay? Certainly Red Mountain, it goes pretty steeply up there. Okay? That's our major landform. The mountains that are there, the plains that are there, the plateaus that are there. And when we do the lab for this chapter, which is going to be Tuesday, you'll see some of these words here. We're going to look at elevations of Red Mountain. We're going to look at the slope. We're going to look at some areas they call plateaus. Maybe even some plains, I don't know, I can't remember any. Those are the broad features, the landforms. There's also minor features, like hills, valleys, canyons. They'll be in between or around or scattered through these mountains, plains, and plateaus. Broad features, the mountains, plains, plateaus. The minor features, the hills, the valleys, and the canyon. We're right at the bottom of three hills. Of course, Red Mountain is up that way to the south of us. Then to the east and the west of us is coming downhill. All the water comes down those three roads and heads to the north of us here. We've had car damage when we've had parked on there and had a sudden really heavy rainfall. Everything gets washed down there. It's torn mufflers off. It's put pine straw up in between the muffler and the bed we didn't know was there. My wife went out to get something. The car caught fire. It didn't actually, the car didn't catch fire, but the materials that were caught between the muffler and the body of the car, they started smoldering, and it was not a good, pretty sight. Okay? There are generalizations of these broad features and minor features. What causes them? One thing is the rock structure. Okay? The second is the weathering and erosion that has occurred. And the third are the stages of that erosion. Okay? Now we're going to look at each one of those separately here. But these, generally, these broad features and the minor features are shaped and formed because of these basic three broad things. Combinations also will come into play. So let's first look at rock structure. The rock structure will determine the shape of the minor landforms. Okay? Now what rock structure refers to is, number one, the type of rock. Okay? Now we remember these from chapter 17. Igneous rock came from molten material. Metamorphic rock was rock that had been something else under greater pressure and temperature, metamorphosized, changed the crystal structure to be harder, denser, okay? And sedimentary rock, these were from the sediments that came out of either particle sediments, called clastic sediments, or chemical sediments that formed usually into layers or into other rock, okay? Rock formed from other rock. Metamorphic sort of was that too. Now, igneous rock quite often is high in iron content. Not always, okay? Granite is not high in iron, but it is a type of igneous rock. Usually is quite hard, fairly resistant to weathering. Not immune to it, but just resistant to it. Metamorphic rock is very resistant usually to chemical weathering. Now I say that there are some exceptions. Remember, marble was a metamorphic rock because it's made out of calcite, limestone. That's very easily etched, not eaten into, but just etched by very strong acids. So our countertops, which are marble, my wife's always fussing at me if I let vinegar or something else spill on there that's highly acid. And then I turn around and say, yeah, but you dropped coffee on it. That's highly acid too. Okay. All right, but never mind. Sedimentary rock is very susceptible to chemical weathering because remember what holds the sediments together? Those cementing agents. And usually the cementing agents are usually sort of alkaline. So if you have acid water, which most of it is, it will break down and chemically weather the sedimentary rocks away. We saw illustrations of that back. So that determines the shape of the minor landforms, what type of rock. But not just the type of rock, what was the attitude? Hey, this rock has an attitude. No, that's not what we're meaning. What that means is the effects of disturbance either by faulting or folding. Okay? What has happened to that rock? Was it bent or folded? Has it faulted? Has there been a crack in it? Was it really brittle? If it was, then what is now facing the wind, the rain, and other things, that's now being affected, the attitude of the rock. What has happened in the past on folding and faulting that is now shaping some of these minor landforms. The faulting and folding often does hasten erosion because things are breaking, and where they break, bonds are not as strong anymore. You got this freshly broken material, water or wind comes along, breaks it faster. Faulting and folding can often hasten the erosion. The erosion then shapes the attitude, makes the attitude of the rock. Okay? Now, number 2 back here was weathering and erosion. That's what we're going to talk about here. What influences weathering and erosion the most? 2 things in general: climate, elevation. Now, climate. Your warm, moist climates, think southeast, warm temperatures, lots of moisture. Thank you, Gulf of Mexico. Okay? Thank you for the warmth from the Gulf of Mexico. Here, your chemical weathering dominates. Really dominates. Because, get this now, most chemical reactions happen in the presence of water. Oxidation is sped up in the presence of water. Acidification or carbonation has to be in the presence of water because it's carbon dioxide mixed with water. And hydration is all caused by water. So most of your chemical weathering in moist climates, that water is a big factor. Okay? But the temperature also matters. I think I may have given you this rule of thumb before, but here's what it is. For every 10 degrees you go above 40 degrees Fahrenheit, 40 degrees Fahrenheit, that's, probably 5 degrees Celsius or so. But every 10 degrees Fahrenheit you go above 40, this is a rule of thumb now, your chemical activity doubles. So if you go from 40 to 50 degrees, your chemical activity. At 40 degrees, the chemical activity is fairly low because chemical activity happens more in warmer situations. You boil things to make things happen. Okay? You heat things up to make them happen. So at 40 degrees, you have very little chemical activity. When you warm up then to 50 degrees, that chemical activity is doubled. Warm up to 60 degrees, it's doubled again. 70 degrees, it's doubled again. 80 degrees, it's doubled again. It's 80 degrees outside now. How much chemical activity is going on? A lot. 90 degrees, it doubles again. 100 degrees, it doubles again. Now, that's normal in the summertime, but think about the wintertime. The wintertime, how many days did we have last winter that were above 50 degrees? I would say most of them. How about up in Minnesota? How many days did they have above 50 degrees? Probably not too many. Okay, so what's my point here? Whereas they get several months of almost no chemical activity, we hardly get a solid month, usually not a solid month, pieced together a month of very low chemical activity, because we're just about always above 40 degrees. Only in the coldest weather do we not get above 40 degrees in the daytime. And I can't remember last winter if we ever had a day that didn't break 40 degrees. So here in the southeast, the chemical weathering dominates. Now remember, I talked about how I like to mulch our flower beds, and other things like this. I have to keep doing it year after year after year. Why? Because the chemical weathering also wears down that pine bark, also wears down the cypress bark, also wears down the pine straw, the leaf mulch. It eats it up. Those microorganisms, they're part of it. Biological weathering, they're eating that stuff up, and the warmer it gets, they double in their activity as well. So, how about the dry climates out west, where this guy's from? Okay? The author, I mean. Mechanical weathering dominates. That's where those ventifacts occur. We drive out there to see the national parks that have these beautiful, beautiful carvings in the rock caused by wind. Okay? Mechanical weathering dominates there. Sharper angular outlines are more common. Think of the Appalachian Mountains, very rounded mountains. Think of the Rocky Mountains, really angular mountains. Okay? Drier climates, more mechanical weathering, moisture climates, moister and warmer climates, more chemical weathering. And the longer you're moist and warm, the more chemical weathering you have. That's why our soils in the southeast are measured, topsoil are measured in inches. It's the rainfall and the chemical activity has worn it out, and we overcropped it for years and years and years. So yeah, it's partly our fault as well. But up north, they have months they go with no chemical weathering at all. Those soils just sit there and stay until the next spring and then start their activity again. Okay. Now we get to stage of development. And this starts at the very end of page 518 and moves into the next page. And if you think you've seen this before, guess what? You have. Only then we're talking about stream development. Now we're talking about landform development. And guess what? They interleave like crazy. Why they set them twice? Why didn't they just put them both together? I don't know. He put them together this way. It describes the cumulative effect of those formative processes we've talked about. The weathering, the everything else that's gone into it. And what are these developments? The youthful development. The weathering and erosion is at the very beginning stages. It's always there, always happening, but it's just beginning in these areas. The mountains now have steep peaks, narrow, steep valleys, V-shaped valleys. That's what your youthful stages of development. The Yellowstone River, V-shaped, that's a fairly youthful situation. The Rocky Mountains, remember the Tetons, very jagged, ragged on top. The steep peaks, that is youthful development. Appalachians, really old, rounded, nothing. They're more mature. Original structure has worn down into rounded peaks and gentle slopes. These slopes are very steep. Here they're a lot more gentle. When you finally get the old age, characterized by nearly flat rolling plains. Okay. And here's a term these two terms here, can't recall seeing anywhere but in this book. The peneplains. These are the nearly flat surfaces. Now here's what I think of when I think of that. Have you been down to Auburn much? When you get into that's sometimes called the wiregrass region, it tends to be fairly flat. Here in Birmingham, everything is judged by mountains, okay, or hills, or really a lot of dissected landscapes. Go down near Auburn, things get really, really flat. Go on further south from there, you get into what they call the coastal plain. Now, occasionally you run into hills, even in these peneplains, monadnocks. Now, I've never seen this word anywhere but in this book. Those are hills of resistant rock. I think, I may be wrong on this, maybe Stone Mountain is a monadnock. Maybe not, I don't know, but that's a hill of very resistant rock. Now, let me give you another example. It probably wouldn't be a monadnock, but I think I've mentioned to you a few times our farm in Georgia. My sister lives on the southernmost end of the property. It's the family house, the one I grew up with from 6th grade until I left. She inherited that. She's pretty much on a clay hill. Okay, there are grady ponds on either side of us. Those are land area where the soil is actually sunk and it's really swampy. My mom used to really gripe and say, why did we build this house in between two swamps that bred mosquitoes like crazy? She hated mosquitoes and they just bugged her like crazy, literally. Okay, but that's where she lives. Across the road from her, then my brother, younger brother, his soils are just about all sandy soils there. That's where it washed down off the resistant hillside where my sister lives, washed down and made the sandy soils down where he lives. It's just right across the road from her. I mean, she lives way off the road, he lives a little off the road, but you can see the houses from each other. Okay? Then we are on a hill, and our hill is some of the most resistant clay I have ever seen. There's some rocks in it too, which make it resistant to change too, but that clay is not going anywhere. I mean, it is resistant. And then my older brother, he's on the northernmost part, and he's again down into very, very sandy area. He's just above the major creek in our area, almost in what you would call the floodplain of it, but he's above that. But everything is really sandy in his area. So just on our farm, and it's not a big farm, you go from clay to sand to clay to sand. And when we've drilled different wells in different part of the farm, my sisters, the one where the house where I grew up, that on a rain is always going to get sort of contaminated a little bit. The water turns red from red clay making its way down into it. The shed that my dad first put there, some of the best tasting water you've ever had. My two brothers sort of in between, we happened to tap into that same place where the cattle shed was. Really good water there. So things change in just a very short times. Now, rejuvenation is mentioned here. Land is always being uplifted, erosion begins again. And usually where an uplift occurs, either folding or faulting, it's more rapid erosion. So things change. They're always changing, just like the rock cycle, just like principle of uniformity. Everything goes through cycles and cycle and cycle. Okay, I think that may be, yes it is, the last slide in the set. Okay, here's another great picture of a valley glacier, and just below it you can see where it's beginning to melt and it's forming and digging out eroding away the crevices there where the rock is a little more susceptible for chemical and physical weathering. Okay, and there you see several of the landforms being formed. Here you see a stream. I don't know what they're trying to show here, but you see the gravel along the side that's been deposited there because the water slowed down and couldn't carry it. And anyway, that's other illustrations of, I guess, landforms. Okay. At the end of the chapter, there is a summary. Let me show you this again. Oh, you almost made me forget my line. Nothing replaces reading the chapters. Y'all are all mouthing the words with me. This chapter has a very, very short summary. That's all, folks. Just that little bit there and the little part at the bottom of the page. One of the shortest summaries out there. Whoa, here comes Andreas. He must have had to go out and come back. Let me see if I can let him in before it blocks me. I think I got him in. Okay, I'm pretty sure I had him here. Yes, I did. Okay. Key terms, like the summary was short. Boy, look at that list of key terms. One of the shortest lists I've seen. Okay. Applying the concepts, though, this is the best thing to study, 45 questions, all multiple choice, one of the best things to study for your test. Certainly those same questions aren't going to be on your test, but most of your test questions will be multiple choice. You'll probably only have around 15 to 20 is my guess. I don't remember for sure. But it covers the same material as this, even if it's not the same questions. Certainly a lot more is covered here than will be covered on the test. But if you know these, there's a good chance you'll know those. Then questions for thoughts, 18. That's right around normal. For further analysis, only 3, a little bit less than normal. And then they mention again, invitation to inquiry, frost wedging. You're probably not going to run into much of that here, so I wouldn't sweat it too much, but you can read about it if you want to. Parallel exercises, again, they're mostly like the examples given in the text, which are, I find, not all that useful. All right. How are we doing on time? Oh, we actually went past 3:45. I didn't mean to, but we did. We're skipping chapter 21, geologic time. Okay, I wish we had time for it. It's an interesting chapter. Let me say this. You might want to look at it. You might get some ideas for paper topic. Even though we're not covering it, you might find that it has some really interesting stuff in it. Okay, so I don't say ignore it, but if you don't have the book with it, you don't have the book with it. But if you do have the big book or an ebook or something like that, then by all means, take a look at it. There are lots of interesting things there. I wish we had time for it. The person mentioned here is Edward Seuss. No kin to Dr. Seuss, I don't think, but he doesn't look at all like I would picture him to be. Austrian geologist who helped pave the way for modern, blah, blah, blah. So if you want to follow him up, you certainly have him there. Now we also are skipping chapter 22, which is the atmosphere of the earth. Now I wish we had time for this, because in chapter 23, which we'll start next week, we're going to be talking about some of the things about the atmosphere. So it wouldn't hurt if you have the book to scan through that, maybe even read it. Okay, more important to read chapter 23, but if you have time, read 22 as well, because there is a lot of good stuff there. I wish we had time to do that one. If it wasn't that some of you may have bought the book from the bookstore, which doesn't include chapter 22, I would be tempted to throw that in this time. But so, because the bookstore was selling the condensed version, I won't hold any of you responsible for that. Person behind the science here, James Ephraim Lovelock. I'm not even familiar with the guy because I've never taught this chapter. English scientist specializing in atmospheric situations. So I'll let you read that if you're interested. We'll be beginning next time, Chapter 23, Weather and Climate. Okay? And it is two really big topics there, weather first and then climate. We'll get about 2.5 hours worth on Tuesday. We'll stop and do the lab for Chapter 20, which we just finished. After we do the lab, I'll post the test for Chapter 20 for you. All right. Any questions? Okay. I think I'll go on and end the slideshow if it'll let me. Okay. Any questions on what we've done so far? Especially Chapter 21, Chapter 20 that you'll be tested on. Well, we'll do the lab on Tuesday and then I'll give you the test. Do you have any questions? Or any past labs? Has anything stumped you? Did you miss some and you need to go back and understand what we're doing in those labs?
I have a question.
Sure.
I believe it was lab number 3, the one where we're supposed to watch the moon, just like kind of keep up with it.
Right.
Could you like go over that like a little more, like when it's due and like how the points are gonna work? Because I know you said something about like we can get like just by filling out like a certain part, we can get certain points.
Okay. I think I understand what your question is. The answer to the first part of it, when's it due? When you're finished with it. Okay, that's the short and dirty on that one. When you're through with it, turn it in. One student has already submitted it, I think. I can remember at least one has. So she was able to get enough observations, and she did. Okay, now the other part I think of your question was most of that lab we did in class. We talked about the phases of the moon. We drew things that dealt with the phases of the moon. We did, so I can't remember now exactly, but it seems like there were at least 6, 8 is 14, and 8 is 22. 14, 36. There were at least 36 questions in that part that we did in class together as a group. Okay? There were only 3 questions based on your observation of the moon. So 36 out of your 39 points are come from what we did in class. Now, I can't do the figuring in my head right now, but I think that's at least 23 out of the 25 points worth of the things. If you did what we did in class, you got 23 out of the 25 points if you got them all right. Okay, whether you do any of the moon observations or not. So don't throw it away just because you didn't get to observe the moon. Or if you got to observe it some, you might be able to get some partial credit on those. So turn it in. Okay, if you indeed, you know, if you still are wanting to make observations, I was out last night and it was sort of cloudy, so I couldn't tell for sure. I never saw the moon last night, so I'm not sure the moon's going to be that visible for the rest of this mini term. Did anyone look at the moon last night?
I didn't see it.
I didn't either. Okay, so it may be you're done for on the moon observations. I can't swear to that. It may come out again that last week, or something like that.
I had issues with that the previous week too. I just couldn't find it.
Yeah.
So I'm thinking about just taking the L on those 2 points.
Okay. Yeah. I mean that. Yeah. Yeah.
I like holding work.
Yeah. So it's up to you. Like I said, one student turned it in, and she got at least one of those questions. She filled in the graph, and it looked really good. I didn't see the other 2 questions, so I don't know if she got observations on that or not. She may have just done one of the 3. I don't recall. But anyway, you've got an option there. You can get the vast majority of the points just by turning in what we did in class. So don't fail to turn it in just because you didn't get to observe the moon. So, did that answer your question?
Yes.
Okay, good. Any others? By the way, I'm willing to stay on till 5:45 or later if you need me to, but I'd rather you work on what you need to work on so you don't have to listen to me, but I want to answer any questions you have on any of the labs.
Hey, Mr. Fowler.
Yes.
This is Keandra.
Right.
I have a question about lab 1.
Okay.
Now, I see the other labs in like the YouTube, lectures and stuff. Where can I find that one? Would it be in one as well, in week 1 as well?
Okay, lab 1, and I did bring up, because I thought we might have questions like this. I think I have PowerPoint here, though it has died on me, so I'm going to have to, yuck, going to have to log into it again. So hang on, it's going to take me a minute or two to do this. I'm not a fast typist. And Blackboard is sort of awkward sometimes to get into. Sometimes it takes longer than others. Okay. Now, here we are. Fiscal, oh, you can't see it yet. Let me go back to Zoom so you can see this. I think it's right there. Okay. Now let me move, you can't see it, but this taskbar is in my way. So let me move this as far out of the way as possible. And because I can't get to my controls here, I got to move Drew out of the way. Drew, you're in the way again, you know that? Okay, here we go. Now, you can't see it, but it does. Okay, can you see my Blackboard here? All right, scroll down to weekly assignment and activities. Okay, click on that. Oh, I'm sorry, you can't click on that. You have to click on the down arrow over here. Okay, week 1. There you can click on that one. And it opens up. Okay, now. Overview and weekly to-do list, that's pretty much old hat. So now, here's where most of your information will be. Every week. Week 1 especially. Click on instructional materials, lessons, PowerPoints, videos, handouts, and so forth. Click on that. Okay, there were the PowerPoint slides for chapter 14. I think we only got to 14. I don't think we got to 15, but I put them there in case we needed them. Here are the recorded lectures, the YouTube playlist for this course. Now, if you remember, the school hadn't paid the bill, so we couldn't do Screencast-O-Matic, which is running, by the way. I have it on today. We couldn't do that for the first, I think, 3 classes. But I left the classes out there from the summer. Not a lot of different. They did the same lab. So if you want to go and watch that, it will be the lab, the class, the playlist that deals with the latter part of chapter 14. So you might have to look at a couple of them to find the one that has that lab in it. I forgot to put the name of it. Now, while we're here, I'm going to mention research paper instructions. Hint, hint. Don't forget to do your research paper. Locator card. That's just when I'm available. Okay? Not so important. These are those beautiful pictures from... Say again? Was there someone say something to me, or was that just your mic came on? Okay. These are those beautiful pictures from Hubble Space Telescope. They're just there. I couldn't resist those. Space Objects in Perspective, another nice little website to go to. Here's that first lab. Now, this first part of it is the evening sky map for August 2020. That's what you base this part of the lab on. Okay? These are the questions. The doc file, the PDF file is the evening sky map for the month of August. Now, if you're wanting to watch it on the videos, because they didn't have the bill paid, I couldn't record this one, but it was from last summer. It's almost the same sky map. It was just June sky map, not August sky map. So you can go back and watch that, and you can either do the lab based on that one, or you can do the lab based on this one. I'll recognize the answers. They're not going to be far off different from each other. So that's what you can do. But does that answer your question? This is where you get your data, and this is where you fill in the answers.
Okay.
Got it? Okay.
Yes, sir. Thank you.
Yeah, and most of the other labs are the same way. I'm going to come up here to get out of this one. Okay. So I'll get out of that one. And the week 2, well, let's see. It's easier to me. I could do it from right there, but I'm going to. Now, I just saw something that reminded me. Okay. You will not find test 1 here under test 1. You'll find your scores there, but you won't find the tests there. Same thing here. I showed you where the lab was. The lab was in instructional materials. This is where your score for your lab will be. Now, I don't have most of these in Blackboard yet, so don't get panicky if you don't see them there. I have been printing like crazy the last couple of days trying to get caught up since I have this many papers to grade from this class. Okay, I've finally got most of them printed. I still have a few more to print, and once I get them printed, that's what I'm hoping to spend most of, well, some of tonight, but mostly tomorrow doing, getting the rest of those printed and graded, and then I'll get them posted on Blackboard. So hopefully by Monday, knock on wood, that maybe I'll have Blackboard at least partly caught up. But just because you see lab here, that's not where the lab is up here under instructional materials. This is where your score is. Your test is over there under Blackboard message. I'll show you where that is. Somebody was asking about this earlier too. Let's scroll up here. There is the icon for Blackboard message. You see it says messages. If you click on that, you'll go to the message, and there you'll see all the tests that I've given you. What is it, 7 so far? Or 6? 6 so far. The one I'll put out there next will be 7. Okay. So that's where the tests are. What you saw here is the grade. You'll also see it in the grade book, and by the way, the grade book is up here. And why they have so much duplication here, I don't know. This is the grade book showing everything, but they show and this is just the crazy way they do this, all this layering. It's just nuts. There was a place for me to put the lab scores in here, so I did because it's easy, but it also shows up in the grade book, and the test scores go in here. They also show up in the grade book. Okay. So now I'm going to get out of test 1, week 1. I just wanted to show, got to go up a little bit further. Oops, up further. Well, y'all are in the way. Matthew, get out of the way, would you? Okay, there we go. I'm going to close week 1 out here. And by the way, I'm going to plan to go in and remove some of these things we never use. I wasn't comfortable doing that at the beginning. Now I don't care. So week 2, again, the overview and weekly to-do list is what we did that week, but here's the materials for that week. And you notice I put 15 again and 16 PowerPoints. When I talked about the recorded lectures, I referred you back to week 1. That's that YouTube. All the files are in that one place, so why did I need to put them every week? They should have had one at the very beginning, and I would have put it there. That's what I used to do. Now they want it every week. So I said, see week 1. Handouts, the research paper instruction locator card, other links, see week 1. Okay, here is the lab we did in the second week. Now that was the one based on the motion of the sun, and again, the YouTube video will be where you'll hear me go through it. I couldn't do that for this time because they still hadn't paid the bill, but I did it for last summer. Same lab, same lab. So you can go and listen to me do it. It's the end of chapter 15, lab 2. Okay? And that's how it goes every week. I don't remember if here, oh yeah, got to close this out right here. Then again, lab 2 will show up here. and test 2. Not the lab. The lab was up here in instructional materials, but the scores will be here. The test 2 will be in the YouTube and the Blackboard message. The scores will be here. Okay. Now at some point we did more than one lab and more than one test a week. So I think when we get to 3, let me see if I can get to week 3 now quickly. Close this one out and do week 3 here. And this is how it goes. You know, you get the pattern of it. Well, it won't open. Okay, some of these things you double click, some of them you single click. Again, the instructional materials, okay. This week we did chapter 16 and 17. Here we did lab 3 and lab 4, okay. So let me go up and close this out. But the instructional videos, see week 1. Research paper instruction, locator card, see week 1. So all that, go back to week 1 to see those things. So down here, remember we did lab, I don't even remember lab numbers now. Lab 2 and lab 3. Well, there's a place for lab 3 and test 3, but lab 2 and test 2, there's no place for it here, so that'll be on the gradebook. Okay, there will be columns for it there. They just didn't have but one place for each here. Again, this is so awkward, the way they put this thing together. Number one, it really wasn't set up for mini-term classes. It was set up for full-term online classes. That's not what we're dealing with here. So you'll see lab 2 and test 2, you won't see in these, you'll see them there, okay, under that. So I just wanted to point out, don't get bent out of shape if you don't see something here. It'll be somewhere, for instance, on the gradebook. That's what really matters. Week 4, instructional materials. And see, we did lab 4 and lab 5 here. Okay. Now this lab 5, I can't remember which one. I think it was lab 5. We needed this website. It is actually called a virtual. I didn't mean to do that. A virtual lab. That's the one that was the plate tectonics lab. You remember that? So everything is there for you. If you read, let me get out of this. Yuck. Okay. Well, I think I got out of too much, didn't I? Yeah. Sorry about that. Do you need me to go back into that, or are we all getting bored to tears? I'm losing people like crazy here. Does anyone want to see any other things like that? Let me know. Any questions on any of your labs, any of the, where you find something, where you go to something, I'll be glad to answer.
Hi, this is Sabrina.
Yes.
I don't have any immediate questions, but I do have to go ahead into work. Is it okay if I email you the questions that I have on certain labs?
Sure. Yeah. That's perfectly fine. Now, remember, I'm a little behind on emails now, so I can't promise when I'll get to them, but I'll get to them as soon as I can.
Okay, no, it's okay. I'm behind on labs.
Okay. We're in the same boat then. Okay.
Okay.
Good deal. Any other questions, issues, concerns? More and more people are leaving, so I'm guessing, are y'all about through, or you want to ask any last things before we leave? What I prompt? Yes. What I hope to do in the time I've got left is to print more things off the off emails, get caught up with my emails, and then once I get everything printed, I'll start grading. Hopefully some of it today, more of it tomorrow. Hopefully I'll get it finished, or at least mostly caught up over the weekend. Anything else? Only got 4 people left. Anything? don't know if y'all are still here or you just left your phones on or your computers on. Okay, take care, folks. Be safe. Have a good, safe, pleasant weekend. But remember, the virus is still there. Don't let up your guard. I hear every week of more people being infected. It's happening. Stay safe. Take care. Unless there's anything else, I will end the meeting for everybody. Bye-bye.